Hello, everyone.
So, good morning, everyone, here in Lecture Hall A, and all of you out there in cyberspace on Zoom. And welcome to this dissertation, where Guanqun will do her best to defend her thesis with the title Versatile Association Behavior in Mixtures of Oppositely Charged Amplifiers from DNA-like assembly of supramolecular helices to coacervation in chiral surfactant systems. I am Ulf Olsson, and it's my pleasure to chair this event today. I will start by introducing sort of the main people here. Of course, we have Guanqun, and then we have the faculty opponent, Mikhail Gradzielski from the TU Berlin. Mikhail, thank you very much for coming here and for sort of doing this job, which I know is not really a small job. There is a grading committee, and you are out on Zoom. And spread out all over the world. In Haifa, we have Diganit Danino, professor at the Technion. Hello, Diganit, welcome.
Hi, good morning, everybody.
In the UK, in Bath, we have Karen Edler. Hi, Karen, welcome.
Good morning, everyone.
Yeah. And then up in Stockholm, we have Per Claesson, professor at the KTH. Welcome, Per. Good to see you. There is also a deputy, and that's Mikael Lund, who is now, but is sitting here in the lecture hall. So in case one of the committee members will faint, and then Mikael will step in. There is also a very important person here, and this is Karin Schilén, who has been the supervisor of Guanqun, and then in the background there was also Vivek Alfredsson as the co-supervisor. The procedure now will be that I will soon give the word to Guanqun to ask her if she has anything more to either add or remove from the thesis. After that, there will be presentations, two presentations. The first one will be by the faculty opponent, Mikael, who will sort of give an overview of the field and sort of try to explain how this thesis fits in the bigger picture. And then I think that Guanqun, you will make a presentation, more detailed presentation of your main results of the thesis. After these two presentations, we will take a short break, maybe 5 minutes. And when we then come back again, it's time for the discussion, main discussion. This is the main event of a thesis defense between the faculty opponent and the respondent, Guanqun. And that will go on and go on and go on. And when Mikael thinks that he's sort of really done and sort of gone through everything in the thesis, then the normal case is that the members of the grading committee also have the possibility to ask some complementary questions to the respondent. And after them, it's actually open to the full public, that anyone can ask any questions that you have to Guanqun. And the people that then on Zoom want, if there's anyone out there not from the grading committee, because you will discuss directly with Guanqun, but if there's someone else in the public that would like on Zoom to make any questions, then you can sort of forward that, do that in the chat of the Zoom. I have anyway also here put down you can read my email address in case there's something particular that you would like to address to me as the chair of this dissertation. When there are no more questions, then this sort of open part of the dissertation closes. And it's time for the grading committee to have a meeting where they will decide whether Guanqun will pass or not. It's their decision from the 3 members of the grading committee. This meeting will take place here in the lecture hall A for those that are here. That means that no one in the grading committee is here. But Mikael and me and the supervisors, we will be here and we will go to a different Zoom link. And those of you now who are sort of on this Zoom link, you would just simply then have to wait until the grading committee is done with their discussions and taking a decisions. And then we'll come back to this Zoom link. And the grading committee will then, the chair of the grading committee will then tell the outcome of their discussions. And then hopefully we can all celebrate. So I think I have said everything that I should say now to explain the dissertation event. So then I give the word to you, Guanqun. Do you have anything that you would like to add or withdraw from the thesis?
No.
Okay, you're happy with it as it is?
Yes.
Good. There's some errata list here.
Yes.
Yeah.
Yeah.
And that everyone sort of can read for yourself. And then I would like to give the word to the faculty opponent, Mikael. And looking forward to your presentation.
So welcome everyone. Okay, welcome everybody. I hope you can hear me. And should be now in presentation mode for everyone. So yeah, as already indicated and stated, my name is Michael Gotzinski from Berlin, and I'm happy to be a member here of this activity today, which is about, as you already heard, versatile association behavior in mixtures of oppositely charged amplifiers, from DNA-like assembly of supramolecular helices to coercivation in chiral surfactant systems. So what are we going to see today? We are probably going to see today, in the end, also a smiling face like here, with someone who's presenting her thesis, title I just gave here at Lund University, Guanqun Du. So what is the topic about? It is about polyelectrolytes and surfactants in principle. That is a topic which comes, of course, from polymer and colloid science, where you combine polyelectrolytes, for the ones who are not really familiar with this field, in principle just a polymer with many charged monomer units, which are put here along the line, and you have many charges. And this is an example here of one of the polymers that was actually used here, the Pampmer, where you have a charge on this amino group. And surfactants, well, surfactants are typically composed of two incompatible components, a hydrophobic one and a hydrophilic one. So that is basically the composition. And someone, as a nasty chemist, put here a covalent bond, so we can't separate and must make something a bit uncommon for simple systems. So you will not have a simple mixture. We will have a tendency to go to interfaces to make aggregates. And here are typical examples. The one which is a sort of classical one, sodium dodecyl sulfate, which you might have used already today for cleaning something. Simple straight chain and a simple head group, a sulfate. And then there is also something more complex like sodium deoxycholate, which we will see from today's candidate a little bit more, which has a bit more complex structure, and for the head group, very similar, just a carboxylate, an anionic head group. And such systems, surfactants, have a tendency for self-assembly, which means due to the hydrophobic effect, so this red part here does not want to be in water, so it will try to escape, and it will escape typically in form of micelles, which can be spherical, elongated, cylindrical. The aggregates can even be more complicated, as we will see today. Why is there something interesting happening if I combine, for instance here, positive polyelectrolyte, a polycation, with some colloidal objects which are oppositely charged? Well, normally you say, well, they are coming together because the opposite charges attract. That's a little bit maybe oversimplifying. In reality, the driving force is the counterions which are released. You gain a lot of entropy by having the counterions going out. So that's really the driving force, but you form bigger aggregates. Aggregates complexes are formed, so it's a way of structuring materials, which also biology does. So it is a very universal phenomenon. And it is a very complex phenomenon if you look a little bit further, because surfactants, depending on concentration, can be monomers. They do not have to be in form of aggregates. They can be in aggregates. They can be elongated. They can be bilayers. So already surfactant science is complex. Then the polyelectrolyte is also a bit more complex by having the charge density along the line here, higher, lower. The charges can be a bit spaced away from the backbone or not. The whole polyelectrolyte backbone can be stiff or flexible, or can be very stiff, like we know from DNA. So there are a lot of parameters that go in, which means each of the both components is rich in its behavior. And then, of course, once you start mixing, it's an almost basically infinite amount or number of possibilities that you can generate. So you can have widely different structures that depend on your components. And it can be individual particles, it can go up to networks. There's a richness of structures and properties. And you have, of course, what you would call a complex, hierarchically structured system, because you have a length scale, which is small of a surfactant, and the bigger one of a polyelectrolyte, and then even more complex situations can arise by further higher order aggregation. So this aggregation then typically leads to different structures where the surfactant might be attached to a chain, it might form complexes. Typically you are looking at this as a function of the mixing ratio, meaning here the surfactant charges, and typically you don't look at just the number of molecules, but at the charges divided by the concentration in total of the charges. And then if you are in the middle range, where you have roughly compensation, you might observe precipitation or formation of coacervates, which are liquid separations. So this would be the normal behavior. Once it's neutral, it might precipitate out. A way to avoid precipitation would be saying, well, I introduce something which makes it still soluble, this starting precipitate. And this is possible by having a double hydrophilic block, for instance, where one is compensating the charges of the micelles, but you still have a block which is hydrophilic enough to keep the whole object in solution. So you retain solubility, and the simplest case here would be, as it is depicted here, a spherical aggregate or roughly globular aggregate. But what about more complex structures? And that's basically the key topic today, that most of what you will see later will be more complex, and we will discuss that. Well, the complexity can already come in if you look at more detail of what happens if you are adding more and more surfactant to an oppositely charged polyelectrolyte. Well, first you might have a little bit of aggregation happening along the chain. It might get more compacted, and at some point when you start neutralizing, here you have a double hydrophilic block, you will form this globular aggregate, as I just pointed out. But then if you look in more detail, if this is sufficiently large, it can become already ordered in a liquid crystalline ordering, and here, for instance, in a cubic order. So with addition of the surfactant, you are successively evolving the structures, making them, controlling them, and also being able, for instance, to have high order at the end. Now, let's move a little bit closer to what is really the topic today, bile salts, sodium deoxycholate. It's a, as I already pointed out, a much more complex structure. It is a more complex amplifier by its architecture. It's also a chiral molecule, which is also an important point, because so far we looked at never the effect of chirality. It is very important to biology. It is involved in fat digestion. It is an emulsifier. It derives from cholesterol. And you see already that here you have more complex aggregation. And you see also that this is a topic of current research. This is a paper from last year that is giving a little bit the details of what you can observe when you have bile salts, especially the sodium deoxycholate, in solution. And you see you can have sponge type aggregates, you can have rods, intertwined structures, foam-like structures, and that all depends on the charge conditions here, on pH, and on the concentration, and on the temperature. So already this molecule alone makes a relatively complex self-assembly where, depending on your conditions, you see different structures. And of course, you see here already that it's more complex because you have hydroxy groups in the molecule that will, of course, affect its behavior and solution. When you look at assembly of chiral amplifiers, you often see that we have a tendency for forming helices, ribbons. This is yesterday was watching the presentation by Canitanino, was already seeing this. She was giving details, so I could refer for all the ones who listen to this talk. You know already a lot about it. But the interesting part is definitely this chirality, of course, introduces the twisting tendency, like we all know from DNA. And you have often then these elongated aggregates, tubes, helices, ribbons, with a certain handedness, right, which arises from the chirality. But it's already clear these are more complex structures than just a simple sphere that we saw for SDS. And here I go now to a little bit more complex version where a different bile salt, the lithocholate, was now combined with a surfactant which derives from it and has a sugar unit here at the end. And you see already this is work which was done by Karin Skelen, Luciano Granantini, and Ulf Olsson, who are all present today. So it is a precursor, you would say, to research that we will see later today, where this combination, this mixture, was already used to tune on purpose the structure, where in this case we see nanotubes, where from the X-ray patterns you can see that their radius can be controlled by the mixing ratio. So it's a very well-defined nanotubes, and because this oscillations here tell you this must be very monodisperse, and you can control the size by the mixing ratio. So one sees, well, this topic is not completely new. So today's candidate didn't jump into the complete open space, which is usually a good idea, but had already some good starting ground. And that the polycation addition has a marked effect, and also just the structure is depicted here. I here took an example where you have phospholipid vesicles, anionic ones, and just by adding under the same conditions, slightly different types of polycations, you see that the formed structures and are looking different. So it makes a difference what type of polycation do you use here, because the interactions are specific. And that brings us now towards the end already of my short presentation here, where I will give a little bit my impression of the, I would say, highlights. There are many points one could discuss, and we will discuss a bit further later on, but some of the interesting highlights which I would see in today's work. And we already discussed a bit with deoxycholate, and our candidate here did the smart choice of using a double hydrophilic polyelectrolyte, a polycation, of course, because you have an anionic molecule here. And this NEPAM is hydrophilic enough to keep the system in solution, but one should also add, and this I didn't go much further, this is a polymer which is thermoresponsive, which means it is well water soluble at low enough temperature. Once you go above 33, 34 degrees, it starts not liking water anymore so much and starts precipitating or becoming insoluble, being more precise. And here we already see that we can observe quite complex structures by mixing, where you see here more spherical objects, but you see already some striped tapes coming here. You see them more here, and you see if you analyze them, we have a very regular spacing. So that's already a much more complex structure than I was showing before, and a very regular one. So it's intriguing how this forms. There was in the thesis and in the paper that belongs to it already an explanation given of our more complex surfactant, the deoxycholate, arranging here, being ordered and making these stripes, and therefore having a well-defined structure, something which is pretty interesting. And it's also an interesting structural equilibrium between a sphere and this complex arrangement. And this was then dwelt on a little bit further by modifying the length of the polyelectrolyte here, sticking to the same system, but at different concentrations. And you see then there's a bundling, but there's also toroidal structures formed. Again, that's very interesting because if you look at it, you find very similar structures in DNA or compacted DNA or DNA toroids. So the point that is interesting definitely in this work, that one can first form these structures and there's a good structural control by the composition. So we have DNA aggregates and now in our toolbox of synthetically accessible colloidal materials, something quite similar. An interesting question, which we probably also discuss in a moment, will be what makes these systems aggregate in this way. As I already indicated, the NIPAM is a temperature responsive polymer, so we can look at its temperature response. And this was also investigated here and published in this paper and in the thesis. One sees that with increasing temperature, you can associate at the mixing ratio in between, where you are roughly at equimolar conditions. And you see in the X-ray scattering curves that the formerly present structures, which we described, these ribbons and tapes, they become bigger and we are more ordered here also. So there's a reorganization into more ordered structures. And a question which I think also came within the thesis, how can this be used maybe for sequestration and temperature cycles maybe? There's much more in this thesis, which I won't be able to tell in all detail, and I won't. But there is also investigations which compare it, for instance, to classical SDS. So you have a reference case in comparison. It forms also very ordered and temperature sensitive systems. Question here is, of course, why is this all this much different to the deoxycholate case? And it is different, but it forms pretty organized structures. And another thing which was investigated in the last part was surfactant mixtures, also a very interesting topic where chiral Gemini surfactant was studied and was combined with a bile salt to give correspondingly, you would say, chirally recognizing systems. But I think this is the point where I would then hand over. I've given hopefully a little bit of flavor of a background and how it comes to studying such systems, which are interesting, which are challenging. And I think this is the time where now the candidate herself can give more details and more insights to us and show what she was having as interesting results here.
Thank you, Mikael. And now I give the word to Guanqun, where you now go through the main results of your thesis.
Can you see my screen? Hello, can you hear me? Yeah. Okay. Okay, hello everyone. Welcome to my PhD defense. First, thank you for Micah for a very nice introduction. Today, I will present my thesis from 4 years PhD study. The title, as Micah mentioned, is a versatile association behavior in mixtures of oppositely charged amplifiers, from DNA-like assembly of supermolecular helices to conservation in chiral surfactant system. First, I will show you the oppositely charged amplifiers involved in my thesis. The first group is cationic diblock copolymers. They are polynipam PAMTMA block polymer and MPEG PAMTMA block polymer. The second group are homopolymers. They are PAMTMA charged homopolymer and non-charged polynipam homopolymer. The third group is the head tier surfactants, which includes the conventional surfactant SDS and the chiral Gemini surfactant. The important member in this thesis is the biological surfactant bisalt. Among all these amplifiers, bisalt is the one that strikes our interest the most. And actually it is the bisalt triggered my whole PhD study. But why are we so interested in bisalt? As I mentioned, bisalt is an important biological surfactant, which works in our body for fat digestion and absorption, and it works in these enterohepatic circulations. During this circulation, 5% bisalt will be lost in colon, and 95% bisalt will be reabsorbed back to continue this circulation. However, if there is something wrong in this reabsorption process, then more than 5% bisalt will be lost. This bisalt malabsorption will cause some bisalt-related disease. For the treatment of chronic diarrhea disease, there are some commercial medicines with polymeric sequestrations which can bind with bisalt to form complexes and thereby decreasing the level of bisalt in intestine. However, there are some disadvantages in the current medicines. For example, they show some low efficacy, poor compliance, and the water insoluble complexes can cause severe constipation for patients. So there's still room for improving and finding new bisalt sequestrations. In addition, bisalt sequestrations can be also used to treat hypocholesterolemia disease. With all this in mind, we were thinking maybe oppositely charged blocopolymer can be a good candidate as new bisalt sequestrations. To see this possibility, it is crucial to study the interaction of bisalt with their sequestrations from physiochemical perspective. And this is therefore was studied in the first part of my thesis, the oppositely charged blocopolymer bisalt mixtures. In addition, the blocopolymer SDS system was also studied in second part to compare with blocopolymer bisalt system. And the chiral Gemini surfactant bisalt system was also involved in part 3 of my thesis. With this background, the aims of my thesis is to find potential blocopolymer as new bisalt sequestrations to treat bisalt-related disease, and also to achieve supermolecular assemblies that can be used in biomedical applications, and especially if these assemblies have some chirality or thermoresponsive property. And also to build supermolecular structures from bottom up by non-covalent interactions of small molecule building blocks. Now I will show you the main result from first part of my thesis. In this part, the mixed complex formation, co-assembled structures, thermodynamic interaction, chirality, and also thermoresponsive behavior in the blocopolymer bisalt mixtures was studied by different techniques. And the composition was expressed as negative charge fraction or negative to positive charge ratios. The mixed complexes formation was studied firstly in these blocopolymer bisalt mixtures. You can see from criteria, we have two types of co-assembled structures coexist in these mixtures. One is the globular-like object. Another one is the strapped tip-like structure. In order to know how these co-assembled structures are formed in these mixtures, the positively charged Pantma homopolymer was introduced in paper 2 to find the truth behind the strapped tip-like structure. You can see from criterion we have a single nanowires formed in these mixtures. And the wax measurement shows 4 peaks, which match the layer line of X-ray pattern for the bisalt helices in a dry fiber. From this, we can conclude that the single nanowires and the strapped in the T-plug structure are the supermolecular helices of self-assembled bisalt molecules. This result also demonstrates that PAMTMA block is critical in the formation of co-assembled structures. So from now on, we will call the strapped T-plug structure as bundles of supermolecular helices. To see if this kind of supermolecular structure is a common phenomenon in similar block polymer bisalt mixtures. Two shorter polyNiPAM PAMTMA block polymers and one MPEG PAMTMA block polymer were used. You can see from criteria bundle-like structures are formed in all these three block polymer bisalt mixtures, meaning the formation of bundles of supermolecular helices is a general phenomenon in similar block polymer bisalt mixtures. In addition, single helices are also formed at low charge ratios. And when we increase charge ratios, the bundle become wider, which means the width of the bundle can be tuned by optimizing the mix ratio in these mixtures. To see the bundle structure from 3 dimensions, the cryogenic electron tomography technique was used as Deganit mentioned yesterday. Here are 3 videos for the from the tomography analysis. I will show you the videos. So from the video, it is clear that the supermolecular helices are packed in a hexagonal lattice in the bundles. In addition to the bundle structure, toroids of supermolecular structure were found coexist in 3 block polymer bisalt mixtures at some certain charge ratios. And the tomography result shows that the supermolecular helices in the toroid structure are also packed in a hexagonal lattice. It is surprised that our bundle and toroid structure formed in the block polymer bisalt mixtures are structurally very similar to DNA bundle and toroid. This means it is possible to reproduce DNA like condensation with supermolecular helices of small chiral molecules like our bisalt NADC. To further understand the co-assembled structure formation from thermodynamic perspective, ITC technique was employed. You can see when we titrate bisalt into polyNiPAM homopolymer, the effective CMC in the presence of homopolymer and the CMC in water are almost in the same position. This means the interaction. Sorry, something happened here. What happened? Oh, sorry for the technical problem. So this means the interaction between polyNiPAM and bisalt are very poor. My computer is dying. However, when we titrate bisalt into the block copolymer, the ITC curve shows 3 peaks, meaning the interaction between block polymer and bisalt. And with the combination of criteria and tomography result, we know that the first region corresponds to the single helices formation, while the second region okay, I will not use this laser point. It's terrible. It's terrible to use this. The second region is related to the formation of more helices and in parallel with the formation of bundles and toroids. Since there's no obvious interaction between bisalt and polynipam block, the third region is therefore corresponds to the demethylation and free mast cell formation. Since bisalt is also a chiral molecule, the chirality in the co-assembled structure was determined by using bilirubin as a probe. Chiral molecules can selectively interact with M or P forms of bilirubin. Showing left-handed and right-handed chirality. For example, when 1 millimolar bisalt interacts with bilirubin, the P forms of bilirubin can be selected. And however, when in our mixtures, the M forms of bilirubin can be selected by our supramolecular helices. The CD results also demonstrate the drug loading ability of the block polymer bisalt mixed complexes. It is known that polynipam is the thermoresponsive polymer. Therefore, the thermoresponsive property in the block polymer bisalt mixtures was also studied in paper 3. You can see from DSC measurement, all the mixtures shows endothermic peaks, meaning the phase transition of polynipam block, and the transition temperature decreases when we increase bisalt concentration, which means polynipam block lose the protection from PAMTMA block. The mixed aggregate formation was also studied by Sachs at 60 degrees. This temperature is well above the phase transition of polynipam. You can see when we increase bisalt concentration, the Sachs curve shows the growth and the structure evolution of the mixed complexes. And at very high bisalt concentration, there's a little peak developed, and which corresponds to a distance of 27 nanometer, meaning the formation of microphase separated nano regions. So the Sachs result demonstrates that large mixed aggregates are formed with ordered internal structure in our mixtures. In order to compare with block polymer bisalt mixture, the block polymer SDS mixture was also studied in part 2, as I mentioned before. Now I will show you the difference in these two systems. From ITC, it is clear that there is a hydrophobic interaction between polynipam and SDS, as indicated by this small CAC number. Therefore, when SDS was titrated into the block copolymer, the ITC curve shows clear that SDS interact with both PAMTMA and polynipam block copolymer and polynipam blocks. So from ITC result, we can conclude that co-assembly in block polymer SDS system was driven by the stepwise electrostatic and hydrophobic interaction. Due to the good performance of bisalt in the block polymer bisalt mixtures, the chiral Gemini surfactant bisalt system was studied in paper 5 in part 3 of my thesis. In this paper, 2 chiral Gemini surfactant S and R were used, and 1 ICA racemate were used. The composition was expressed also as negative to positive charge ratios. From turbidity, optical microscopic, and visual inspection, we can see 5 phase transitions were found in these mixtures. They are Gemini-rich mixed aggregates and bisalt-rich mixed aggregates at higher and very low and very high bisalt concentrations. In the intermediate bisalt concentration, 2 conservation phases were found. And the conservation is a liquid-liquid phase separation process, which contains a dilute liquid phase and a dense liquid phase. The dense liquid phase can be also seen as the droplet under optical microscope. The chirality in these mixtures was also studied by using bilirubin as a probe. You can see due to the conservation, the chirality of S Gemini surfactant was enhanced and the chirality of R was become switchable. There is no chirality in the racemate since it is a one-to-one mixture from S and R. However, the chirality can be induced with the addition of biosalt in the conservation region. With this result, I would like to give the conclusion to my thesis. In the first part, supermolecular helices are formed in the mixtures at low charge ratio. And these helices can condense into DNA-like bundles and toroids with hexagonal arrangements. The supermolecular chirality of the helices highlights the potential application of these assemblies for drug-related applications. And the composition control the thermoresponsive behavior in these mixtures turns the aggregates into versatile nanomaterials. In addition, the formation of water-soluble mixed complexes demonstrates the possibility of using oppositely charged block polymer as bisalt sequestrations. In the second part, we found that SDS interacts with both PAMTMA and poly-9-PAM block of the copolymers, while bisalt molecule prefers to interact only with PAMTMA blocks. The co-assembled complexes with ordered internal structure in these block polymer SDS mixtures through stepwise electrostatic and hydrophobic interactions. In the third part, foul phase transition regions were found in the Gemini bisalt mixtures, and the conservation occurs in a broad range of composition. And the chirality of 3 Gemini surfactants can be enhanced, switched, and induced by the addition of bisalt molecule. With this, I would like to thank my supervisor, Karen, co-supervisor, Vivica, Dom, Luciano, Alessandra, Edin, and Boo, and all the collaborators for their help, support, and encouragement during my PhD study. I would like also to thank all the funding, especially my CSE scholarship, for the support of my PhD study. Thank you all for your attention. Thank you.
Thank you, Guanqun. Now it is, we will take a short break,
Yes.
roughly 5 minutes. So I read that the time now is exactly 10
10.
o'clock. So 5 minutes after 10, we will then reassemble, and then it will be time for the discussion.
Yes.
So,
yeah.
Welcome back in 5 minutes.
Yeah.
Yeah. So now we are back, also with the sound. So this was a long 5 minutes, but we now are ready to start the discussion. And Mikael Guanqun, I leave the floor to you.
Here, but it is not a sort of overloaded or anything. It is just showing. But apparently, we very many and very good and interesting results. So definitely a very nice work there. And I would also say also quite a bit of congratulations to the
Thank you.
And so on. As always, you can research this your thesis, but it won't work in science normally.
I'm sorry, I barely hear you.
Okay.
It's on. Can you hear me also?
Yes.
Can you hear me?
Yes.
We can't hear Michael.
Did you mute yourself in this? Did you mute yourself?
No.
No, it's on.
No,
Michael seems to be
hear
muted.
Michael, but very, very faint.
No, you mute yourself. Now
Mute
it's on.
yourself?
You can try. Yeah, here is mute. So
Okay.
you need to
Ah,
push
okay.
it.
Sorry.
Yeah.
I was just seeing the green light and I thought, well, this is all fine now. But the green can be greener. Hopefully now it's better.
Yes. Yes,
Okay.
thank you.
So definitely was a nice piece to read. And it's also, I think, of course, as always in science, when there's a lot of points that one reads, but one says, well, there is a lot of interesting aspects in it, which one could discuss further. And that's what we are probably doing now the next, let's see, roughly an hour or so. And I think when I was reading it and also in my presentation pointing out a bit, I think an interesting part when one looks at the bile salt aggregates is, of course, the difference to a simple surfactant. And the difference to the simple surfactant, typically simple surfactant has just an alkyl chain, maybe a second one. But your sort of hydrophobic part contains hydroxyl groups. You didn't really go much further into it, but maybe that's a point that one could, as a start here, also a bit discuss. How much would you think this will affect the self-assembly properties? Because normally you would say, well, this is all happening because hydrophobic effect. The alkyl chain, for entropic reason, wants to avoid being in water, so they stick together. That's it. But now you have a little bit a different situation because the OH groups in your hydrophobic part will also probably try to be happy, and they are not automatically so happy if they don't find something similar around them. So can you maybe say a little bit what is your feeling about what this molecule then tries to do in such an environment and when it wants to assemble?
Yes, the bisalt we used is NADC with these two hydroxy group in the hydrophobic part, right? According to the literature, this bisalt can do the methylation from stepwise methylation. They form small pre-mast cells by the hydrophobic interaction with very little aggregation number, maybe 1 or 2. Then they start to form the mast cells, stable mast cells with some hydrogen bonding interaction. Then this hydrogen bonding interaction can form this hydroxy group of this NADC. And we also actually tried the different bisalts. I didn't include in my thesis. We also tried NAGDC. NAGDC, they have, it has the 1 more OH group in the hydrophobic part. And we also tried another one is NAGC. NAGC, it has a different head group with this imine NH group. That also has 3 OH group in the hydrophobic part. So we compare these 3 bisalts in our mixture, block polymer bisalt mixtures. Actually, only NADC form this bundle structure. Then the other 2, they can form some structure, but they form some like looks like a sphere or irregular structure, which means, I mean, NADC is the most, compared to among the 3 bisalt, NADC is the most hydrophobic bisalt. Then NAGC is the more hydrophilic. NADC is in the, NAGDC in the middle. So which means hydrophobicity in the bisalt is really important for the formation of this cutoff structure. I have the criterion result if you want to see that.
No, I think I believe you for sure. And was just, but why did you not include then this in the thesis here?
Yeah, this part actually we did a lot with different bisalt and also different temperatures. They also show different thermoresponsive behavior in the block polymer bisalt mixtures if you use another 2 bisalt. So this part actually I did in the first year of my PhD study, but we haven't, the manuscript is not ready.
Okay.
So, and I have too much to write in the thesis. That's why I didn't include that part.
Okay. Oh, well, it's not really a complaint that the thesis doesn't contain sufficient material, but it sounds also like an interesting observation where you say, well, it is very specific for the DC that it forms these type of structures and is not really so generically happening, and you have a lot of effects of adding or having other bile salts. One idea one could then also have, but this is of course making it even more complicated, whether you could have situations by mixing a certain amount of one of the other bile salts for tuning potentially the structures here.
This is a really interesting point. You can mix like a
but you say, well, exactly
different.
what you say, well, I'm using 5% of this one, and that could also be interesting. Brings me also to one other point. I mean, your thesis is much focusing on NIPAM and the thermoresponsive properties.
Yes.
What you are much less showing here, that of course you have also pH responsiveness, not of a NIPAM, but of your surfactant, because that can go all the way from being neutral to being the anionic that you used basically here. But I would also expect that pH should be an interesting tuning parameter in these systems.
This is definitely a critical point, as I can also use this to answer your first question. Compared to these 3 bisalt, NADC is more sensitive with pH, and the other, that's why NADC can form this gel at like a neutral pH 7.1 or something. As I mentioned, this NADC helices is drawn from the NADC gel, but for the other 2 bisalt, they are not so sensitive with pH. So one point could be why we form this bundle structure is also because our mixture, the pH of our mixture is roughly 7 or 7.5. It's more close. It's quite low for NADC to aggregate, especially in the inner bundle. Then for the pH responsive, of course, we can use buffer or something to control the pH. But since we have such complicated system, we don't want to involve some extra ions to to even more complicate the system. That's why we didn't use buffer to keep pH. And we measured the pH is like a 7.5, and we measured the pure component. That's why we think it's 5. The pH is 5 for NADC to soluble. If we go to low pH, NADC bisalt will not be soluble in the mixture. But in our case, they are 5 with pH, so we didn't adjust the pH. But this is definitely a point, because I have also another project, but I don't have time to do that. Is with a pH responsive block polymer. With this PO block polymer, another charged chain. And we didn't do so much there. So there we want to see the really pH responsive behavior in the block polymer bisalt mixture. Yeah.
Very good.
Yeah. Thank you.
No, I mean, this is always, I mean, as I was pointing out in my part of presentation, that you have a lot of cost tuning parameters already by combining. And in reality, you have a lot more, as you were showing. In principle, you could take up a next direction now, where would be parameter temperature, not just the mixing, you have a parameter pH. And if you then, in addition, have a pH responsive polycation, then of course the effect becomes more dramatic. Because both at the same time are changing.
Yes.
And the relative change over a window is becoming bigger.
Yeah.
So yeah, so as always in science, I mean, you can do a lot of work, but there's still plenty of more which could be done, which you identify quickly. Good. An interesting point, definitely, I think, when I looked at the paper 1 here, was the one where you have this equilibrium and structural equilibrium between small spheres, big tapes.
Yes.
What is the explanation of having quite different structures in there? I mean, you demonstrate you have them, but intuitively one would say, well, this is one kind of mix. Why doesn't it decide for one favorite structure, like many systems would do? As a decision structurally, this is the best one. And here it says, well, a sphere is okay, and with big bundles are also okay.
Yeah, this I can answer. It's because this in first paper 1, we use this polynipan 120 and PAMTMA 30, right? This polymer, the pure polymer solution behavior is quite complicated. In the pure polymer, they exist at room temperature. They exist the unimers and also the multi-chain clusters. So I can see when we mix with bisalt, the bisalt could be bind to these 2 kind of structures, like the unimers and the clusters in a different behavior. Then it could form different structures in an equilibrium state. For example, maybe the single chain, they bind with bisalt can form this structure. Then the clusters, they prefer to include some bisalt molecule to form this globular structure. Then they are like equilibrium each other in the charge ratio 1 composition at room temperature.
Yeah,
and also another things, and also we measured the electrophoretic mobility for this charge ratio 1 sample. We see the electrophoretic mobility is slightly positive. That is charge fraction 0.5 is slightly positive, which means even though we have a theoretical charge ratio 1 composition, but we could have extra PAMTMA or extra polymer free chain in the solution. And from criteria measurement, we see mostly this globular structure. They looks like to be close to this frame of the grade. If you look at the figure 4a, they are more close to the frame. As far as I know, the frame, the grade was treated to be negative charged, which means this globule could contain extra positive charge. That's why in the electrophoretic mobility, this positive value can be contributed mostly from the globule. Then the tip can be charge neutral. Then polynipan block on the surface can stabilize the structure.
From the electrophotic mobility, I mean, you are giving the average value, but when you look at the total spectra, do you see anyhow that there is visible two type of aggregates as well with different electrophoretic mobility, or is it sort of just one?
You
peak?
mean when we measure electrophotic mobility, we can see the distribution of
Well, you see what is the fraction at a certain electrophoretic mobility. I mean, you can transform it in also in a theta potential where you see how what's the probability. Do you have just one peak? Is it a broader peak, less?
We didn't really, we measured electrophoretic mobility first. I didn't really focus on to see the peak in the electrophoretic mobility measurement. That is afterwards when we see the criteria. I was thinking maybe it's because of this. The global could.
But then it could potentially be interesting to look more carefully at the original data to see whether there is also an indication that you see maybe
yes.
differences. I mean, the average can still be the same, but there might be a splitting or not, depending on that. But it would anyway, I mean, talking about splitting, I mean, one would normally expect that, of course, the spheres and the bundles are not exactly of the same composition. Okay, you have a mixture, and therefore you would say that probably it's a little bit a different composition in one and the other. So it has a tendency to do with different structures. Did you ever attempt there to try to figure this out in more detail, which is not simple, but it would be an intriguing question somehow. Is there an enrichment of maybe the polymer or I mean, also the polymer is by itself a mixture that is having different molecules in there because you only have a distribution of chain length. So there will be a little bit longer ones here, a little bit shorter ones here. That this could also start, of course, or be one of the driving forces in making the structural differences.
We actually did some like assumption or calculation for this globular structure. We assume if there's no water in the core, the global we thought is this co-share structure, like as a classical polymer surfactant system. If we assume there's no water in the core, because the size we can estimate from criteria, and this is quite difficult. I mean, accuracy, you can have contrast different, you can have different, a little bit variable in size. So if we estimate the diameter from criteria, we can estimate that is the core, because core with this pumped block bind with bisalt is more high electron density. Then we can see the core. The polynipalm is too low electron density. We can't see the share in the criteria. If we assume there's no water in the core, then we estimate the aggregation number of the copolymer of the copolymer chain and the bisalt. They are like 174 copolymers in the core, then 5,220 bisalt molecules in the bind with pumped block in the core. And this, of course, this assumption, I mean, we think it's no water. Of course, there is some water inside, but we can't do the estimation by consider the water. We can't calculate how much water molecule inside. Yes, then for the share for the polynipalm block, if we consider the share, the polynipalm block stretch in the bike solution, then we calculate this this length, the polynipalm length, as this Carton length. I think we Carton length of or Flory radius or Carton length. Then we are able to know this global in criteria. They are like integrated together because of shorter distance. They
Mhm.
are not like a separate, they are integrated. That's why we see the global is quite regular in the grade, because they are like stuck each other. If
Yep.
they are not regular, then they are free. I mean, the distance between two global, they are more like, if it's longer, then they are free. Then we will not see the
Mhm.
regular arrangement in the grade.
You were just indicating that you don't really know how much water is in the core.
Yeah,
You have any idea how you could address it? For sure, you will not see it from the cryo-TM, but there would be a method that would directly tell you it's not off the shelf, so it's not a complaint that it wasn't done here, but one method would directly see that.
Yeah, maybe if we use the first thing is
You
to
did
see
X-ray.
to see how much water in the core.
The X-ray
We have
scattering
to-
doesn't see it, but there would be a method which would see it.
We have to see how much water in the core. First, we have to separate these two structures. We have purely global structure in the mixture. Then we can measure self-diffusion of NMR. Then we know the confined water in the core, then the free water in the bulk. Then we know maybe how much water.
Yeah, this could be
inside.
could in principle work out. It just depends maybe on the ratios, but the neutron scattering would. If you,
Yeah, also the neutral scattering.
if you would
we
vary the amount,
deuterate the polymer, and then we know everything. We know where is the polymer chain, where is the water and the bisalt. Yeah, then we will know everything.
But-
This actually we wanted to do before.
you have to wait here until maybe ESS comes up. So,
Yeah.
well, in the system, I think very interesting other observation was, it's still about this mix of spheres and bundles, that you described that you were filtering them.
Yeah.
And you saw basically exactly what you should not normally expect.
Yeah.
Because normally I would say, well, if I see this and I would have the same idea as here you had, I filtered, probably your idea was mine. I filter out the big stuff and afterwards have the small ones, and therefore have separated them. But you describe, you see the opposite. You filter, and afterwards the big stuff is still in, and the small one is gone.
Yeah.
Any comments to this sort of, you would say, completely, I wouldn't say nonsense, but in principle you would say this is exactly what you do not expect. You're not filtering in order to get afterwards the big things out. It's like I have my coffee filter, and the coffee is remaining up, and down in my pot is the powder. No, that is normally not expected, but you observe it.
Yeah, yes, the beginning purpose is we want to separate these two objects.
Mm-hmm.
We want to like filter away the tip, then we can know the global, then we are able to measure the mobility and also maybe estimate the composition. But we get the opposite result. We actually have the tip again after filtration. I can think, because in our case, I mean, this is the soft matter. It's like a dynamic formation in the solution. And also, if you look at the cryo-TM image figure 4 and figure 4b, the bundle, they are not so stiff. They are, I mean, a little bit flexible. And the scale bar is 200 nanometer. We use the filter 0.45 micrometer, which means 450 nanometer, right? If you can see that length could be this width of the cryo-TM. And if you see the thickness, the bundle in this mixture, they are quite narrow. I mean, they are quite only with like 3 or 4 straps in the bundle. So then after filtration, we are not filtering the hard stuff, the hard object. We are filtering the soft object, which means one reason can be the tip we can pass through. Some of the shorter tip, they can pass through the hole. Then the global can also pass through the hole. Then all the composition changed after filtration, because you may lose some material. Then the left material in the mixture after filtration, the composition can be the optimal composition for the tips, like for the tip structure to form. Which means the shorter tip can go through. We may also break some long tip to short tip, then it goes through. Then some very long tip can stay on the filter. Then you change all the composition, then all the materials in the solution, then they redistribute, then they equilibrium. Because after filtration, we also equilibrium for a long time. Like then we have this reformation of the structure.
But this is another point which I would ask you. I mean, is there good evidence that this is really in equilibrium? Because normally you expect, I mean, you say you equilibrate, which means typically you wait a day or two and you say, well, there's nothing changing. But one must be honest. I mean, we have as humans a sort of certain limited time span which we use for equilibration, which means if things happen faster than I don't know, half a tenth of a second, you don't notice. And if it is more than a couple of weeks, you would say, when I lose interest. Could it still be that this is more slowly acting? Because when I was looking at it, also wondering just yesterday evening afterwards, how much could it be that maybe potentially it's all not really fully equilibrated, and that your filtering might see that you are shearing the system?
Yes.
And the shear, that there is maybe even a shear effect, and that might have a long re-equilibration time.
Actually, this is definitely a point to do the maybe kinetic study. For example, you mix very short, like a second or 1 hour, then you measure critium or you measure SAX, then you wait for 10 hours, then like you do the time.
Yeah, or you might think about even microfluidics.
Yeah,
because
the stop flow.
that you do it in the microfluidics and you make this mixture there, where with the shear, there might be an effect even that your bundles become, I don't know, longer, more, less, I don't know. It's not so clear because this filtration experiment is already a bit strange, but you would potentially even have an effects which then would indicate that this is not really just an equilibrium question, but depending on the preparation.
Yeah, the preparation, this is also a point. Like we actually mix the stock solution directly, then I add extra water, then I stir the encode room for like 24 hours. There's also other mix step, like you mix a 1-to-1, or for ITC measurement, we can't control ITC, we touch it like a 3 microliter jaw plate, 1x1 45 jaw plate takes like 7 hours to finish one measurement, which means the preparation way in ITC is quite different from just direct mixed, right? But we did the SAX measurement for the direct mixture, the normal procedure I did, and also the solution after ITC measurement. We all see this helices signal and also hexagonal peak, which means these two different ways, at least from SAX result, these two different ways, they are not so, different, cause the different structure. And also, if you think about ITC measurement, one scan takes 7 hours. 7 hours is enough for the equilibrium. And also every jaw plate, we have 10 minutes equilibrium for every jaw plate. Then for the direct mixture, we take like I stir slowly for 24 hours, which means 7 hours, 24 hours at least is enough for this bundle structure formation. But as you said, maybe 10 seconds or use stop flow with combination of SAX or sounds to see really how they form this from the kinetic way. Then we really know the mechanism, how they form this bundle structure. This is really interesting. We already actually discussed a little bit. It's a really interesting, maybe future project.
Yeah, I mean, this formation would also definitely be very interesting. Because then you would understand how it works, and that would also allow you potentially to interfere, because once you know the pathway, then you would a little bit like in classical chemistry, you use a catalyst for modifying, but
Yes.
that requires always the knowledge of how it works from the beginning. Otherwise, we would design a catalyst that optimizes a step
Yeah.
that is uninteresting, so which would be not useful. So definitely a good point.
Yes.
Still, the point about the composition, I mean, when you say it's all in equilibrium, when you would say, well, there's probably the compositional differences. Any idea? I think it's not simple to separate the spheres from the bundles, but in principle, I mean, one could try this as well.
You mean separate this global and the bundle structure. In paper 1, we actually only did the criterion for charge ratio
because you
1.
tried with the filtering, but the filtering apparently
doesn't work.
doesn't work. So but one could think about alternatives.
Yeah, we actually don't. In principle, in another indicated from paper 2, we did the different charge ratios by criteria measurement, right? We see all the bundles.
Mm-hmm.
And we see this single nanowires at very low charge ratio, right? With very, very little bisort. But in paper 1, we just did the criterion for this one sample charge ratio 1. We could do at very, very low charge ratio in paper 1. Then we use criterion, we must have some difference. Probably we see global or only tip, or we do very high charge ratio. Since in paper 1, this polymer is quite longer than the polymer we use in paper 2, and the behavior could be different. So, I mean, polynipam is very important to stabilize the structure. So we have 120 in paper 2, we only have 48. So polynipam can play some role to form this global.
For sure.
Since we think the global, they are like a co-share structure, polynipam on the surface. So which means polynipam is very important for the global. So if we go to very low charge ratio, probably, I don't know.
Yeah, but even if you are in a very good charge ratio for having both, I mean, you could start nonetheless thinking about separating the spheres from the big bundles. I mean, not with filtration, but I mean, there are other methods to do that. If you think here, especially in Sweden, one classical method would be that one could try.
You mean this? I don't know if it's correct. You mean, for example, they prepare this
very simple classic. Very simple classical. Very simple classical method for separating bigger and smaller objects, and largely associated with Sweden, with a very famous Swedish scientist even.
You mean this
centrifugation?
Oh yeah. Yeah, this actually we did.
And what happened?
We didn't do for this paper 1. We did in paper 2 in order to get a Sachs signal, this hexagonal peak for the dilute mixture, direct mixture. We can't get this hexagonal peak. This actually I suffered for half a year to get this hexagonal peak. Finally, we find a way to centrifuge the structure, to concentrate the structure. Then we measure the bottom face to get this. Then by use this sandwich plate, then we get this hexagonal peak. So which means even though we centrifuge, the bottom face is also this bound. Of course, in paper 2, we didn't see this small global structure. Of course, after filtration, we only see this bundle structure. But there's another system, also not included in my thesis, with another cutoff block polymer with PO, PDMI block polymer. This one, we also can form some bundle structure and also bigger global structure. The global size can be 100 or 200 nanometer. It's really a global. Here in paper 1, it's like the size is only 21 nanometer. So for this big global and the bundle in another block polymer system, we can use centrifugation, really separate them. After centrifugation, we measure the Sachs and also criterion, the top face and bottom face. So we see in criterion top face, mainly only global structure, and the bottom face only this bundle structure.
And are we chemically different? No, is the composition then different? I mean, you could now analyze how much of a polymer is in there, how much of the DC is in there.
But this, because we don't really know how much global and how much bundle after centrifugation.
But you say you have an enrichment in one and
Yeah,
the other.
We after centrifugation, we see, but from criteria, you can't really do this quantity.
No, but you could just, I mean, centrifuge a large amount, separate it, and then just make a
You
chemical
mean,
analysis.
Yes, if it's a large amount, then you can estimate maybe.
I mean, large
volume.
amount depends on the method you use afterwards. I mean,
Yes.
I would not think, I mean, probably you have a good chance with the NMR, and when you don't really need gigantic amounts, some other could even use less.
This we actually NMR also tried for paper 2, because for paper 2, our purpose, we want to see this bundle structure, right? We think we have some nano channels inside, then water can trap inside. That's why we use some the diffusion MR to really see the different state of trapped water and the free water in bulk solution. But since we have very little volume fraction in the bundle structure, so we can't see the signal. And if we know that, we can maybe calculate the amount, composition in the bundle structure. But in this, as you said, in this another block polymer, we can really separate the big global and the bundle on the bottom face. Then we can do NMR for this top face and the bottom face. Then we can really know how much water in the global, how much water in the bundle, probably. And this also need a high concentration, I guess, but we haven't tried this, but this is the direction for the future work. This we collaborate with Warsaw. So
okay, so the ratio is not so obviously strongly changing with the charge ratio. I mean, the ratio of the bundles to the spheres, which is anyway not so simple to determine, but you might have a little bit of a handle with the Sachs curves, because I think quantifying from the electron microscopy is always a little bit shaky, between shaky and not really reliable, because you can never guarantee so easily that what you see is really the statistical average. But when you change the mixing ratio, what is roughly the impression in terms of, do you see more bundles with more collate? Yes, I think so.
Yes, in paper 2, if you see this 65 poly-9 block polymer, if you go to page, let's see, page 139, if you see figure 1DEF, we show the bundle growth, right? We didn't.
Yeah, it becomes wider.
Yeah, become wider, and this is for the bundle structure. If you go to figure 2, B and C. B is this for 65 block polymer, and in this block polymer we have this toroid structure at charge ratio 0.5, but this small toroid in figure 2C, they are in charge ratio 1. And in MPEG polymer, this big toroid, they are in charge ratio 1. So in principle, we didn't do a systematic study to keep one block non-change to change another block, then really see how the toroid formed. So we can synthesize, for example, we synthesize a series of block polymer. We keep the PAMTMA block non-change, then we change the poly-9 block, then we prepare different charge ratios, then we measure criteria, then we are able to find some clue. Or we do opposite, we keep the poly-9 doesn't change, then we change the PAMTMA block. Then we can also find some evidence. But for now in paper 2, we don't really focus on, we can't, because the polymer we can't synthesize in the series rate. So we didn't focus on how the toroid widely forming in this charge ratio, widely forming in that charge ratio.
Yeah, but this is very nice, because this would be now anyway on my list of questions which I would still have. Because exactly this figure that you were pointing out, I mean, you see the width of the bundles increasing with the collate,
Yeah.
which is a nice finding. So you can control the structure, but still, for when I see this, I would always then have the next question. Can I directly understand that in a more quantitative fashion? Because what stops now the growth? Because it looks always in your images, which you show here, that you have a certain mixing ratio and you have a relatively well-defined width. It's not perfect, but this you also would not expect normally for a normal assembly, because there must be some fluctuations in there, but it's a clear trend, it's a clear control. And there's a clear stopping in growth. Because you could say, well, if it wants to be in one dimension growing, why doesn't it go forever? I mean, you see clearly that we have a very marked spacing, which means there's a certain distance much preferred, which if I transfer this in a sort of energetic landscape, means I have a very marked minimum. I want to be here. The next one also wants to be here. And then the question is, why is when at some point this tendency over? Why is it fine for 3, 6, 8 bundles to be aligned?
Yeah.
And when at some point, but not the 9th and not the 10th. What stops me? I mean, I see this for here in the row. If this would be filled, there would be, I don't know, 11, 12 people sitting here, and the 13th one can't because there's not a seat anymore.
Yeah.
So it's obvious. I understand why there is not 20 people here in the first row. But what stops this bundling, and what tells the system, well, it's fine with 6 or 8 or whatever?
First, the bundle structure as our model showing. We think the inner of the bundle was packed by this self-assembled bisalt, only the self-assembled bisalt molecules, since the distance between two bundle, or distance between two helices, they are almost the same as pure bisalt liquid crystal hexagonal phase at very high concentration. I calculate that 39.18% is like 150 millimolar. Then they form this liquid crystal phase with the interhelix distance the same as ours, which means our bundle inner structure is the bisalt self-assembled molecule. Then in the outermost layer, then the pumped block can penetrate in the outermost layer. Then the polynipam block, they are like free on the bulk solution. Because in our block, polymer pumped block is quite short. We only have 20 polymerization degree. That length is very short. They can't penetrate to the very inner bundle to stabilize the bisalt. And this is our model. If based on this model, if we think about, that's why we don't have a perfect hexagonal because if we have perfect hexagonal, the inner is too far from the pumped, so it's not stable. That's why the hexagonal seems look like a little bit flat, right? Then we are thinking maybe if it's flat, then it can grow like forever in this direction,
exactly.
the hexagonal. But why we didn't see that? Even though we see the growth from charge ratio 0.5 to charge ratio 4, we see the growth in this direction, right? We didn't do like charge ratio 8 or 16 something. But I already saw a sign in charge ratio 4 after half year. We did a criterion again. We saw the bundle, the wide bundle already break a little bit, because if you also can see actually in figure 1F, you can see the some end point of the bundle, but you can't really see the end point from D and E. So you can't really see the end point for the low charge ratio, but you can see some end point at charge ratio 4, which means at charge ratio 4, the bundle, they grow in this direction, but they already start to like a break in this longitude. So why then we are thinking if we increase the charge ratio until 8 or 16, then the bisalt concentration is very high, like higher than CMC. Then can be due to this high ionic strength from extra bisalt mast cells. Then the structure could be dissolved or break due to this. Then finally, at very, very high bisalt concentration, now it's like a pure bisalt bisalt mast cell solution, then you will not have any bundles anymore. So they can't adopt the bisalt forever. This was also indicated from ITC measurement. In ITC measurement, you remember in the third region. In the third region is already after charge ratio 1. We see this big peak. There's no obvious interaction between polynipalm and bisalt. So we dedicate this peak to the bisalt demycilization and mast cell formation, which means at that region, we already have free bisalt mast cells. And that region is roughly charge ratio 3. And charge ratio 4, we see some like a break of the bundle, which means the bisalt mast cell already play some role in a high charge ratio. So then I can foresee at very high bisalt concentration, the bundle can be maybe dissolved. As normal polymer surfactant system, you add a high surfactant concentration, then the polymer can dissolve.
Yeah, this is probably very likely to be expected. What I was just wondering in between while you were talking now, did you ever make experiments where you varied the ionic strength of a solution?
Yes, we didn't. Yeah, if you look at figure in paper 2, we add actually in order to further understand the ITC results, we add sodium chloride to the when I do the ITC measurement, we add 50 millimolar because we don't know how much. Then I just add 50 millimolar. Then if you look at the figure, yeah, page 166, figure S25D. So we add 50 millimolar bisalt. You can see this unfilled curve. Unfilled curve is the ITC curve without with 50 millimolar salt. You see the peak in second region was lowered compared to the red curve, which means the electrostatic interaction was screened by this 50 millimolar sodium chloride.
But you did not check what the structural, whether there are also structural differences, or
we have in figure S26.
Yeah.
Figure 26. This is, we also measure the critium with the 50 millimolar sodium chloride. You can see very clear the bundle become narrow compared to in page 139 figure 1E. And in 1E, you see in one bundle, we probably have 10 helices, but in figure S26, we only have 3 helices in one bundle, which means the salt, they screen the electrostatic interaction, then they screen the co-assembly process. Then they don't, I mean, the helices can't condense into together in a wide direction.
But this is exactly the point where I would say this is an interesting finding in that respect. To the question before of what stops or what determines the size, I wouldn't have an answer here either, but I mean, it's clear that you should have somehow a competition of forces. I mean, whenever you find a maximum, there's something which likes to go there and something which stops it, which means you could think, well, there might be sort of attractive forces coming from the binding together, but then you might accumulate by condensing more and more sort of residual charges, and that would be a point that would then at some point say, well, now I've accumulated too much charge because you simply increase the density, and then at some point, if you calculate, this becomes very marked. But it doesn't seem to be the answer here, because your salt effect, I would normally expect, then goes the other way around, that the salt would then favor, because it weakens the electrostatics maybe a bit. So it's intriguing, but it should somehow be involved with having opposite tendencies that then say, well, and now I bring you to this maximum here.
We should actually do a series of salt concentration to really see the bundle like dissolved into single helices, then dissolved completely. I mean, if we add different concentration of salt, we might see the structure from critium or ITC, which, for example, which peak the peaks in region 1 or region 2 completely disappear or or become larger something, then we can get some conclusion, the salt effect. But we only test one salt. Yeah, this can be done in the field, maybe.
Yeah, question. I mean, it's always what is most interesting. I mean, you have always a lot of things which you could do, and then have to focus on what's most interesting. What I
Yes.
found very interesting here is also the other point that you already mentioned, with toroidal structures. I mean, these toroidal structures are sort of normally not so much expected. I mean, most of the time the bundles, you would still say, well, there's not so surprising when you know already that the aggregation behavior of the deoxycholate is to form something which is sort of one-dimensionally growing. You would say, well, it's not surprising that it modifies but sticks to this idea. But it's more interesting when definitely when it does not stick to this idea and says, well, also forming a nice circle is a good idea. And so I would have basically already two questions. What would be your answer for what motivates the system to make these toroidal structures? And secondly, what you also show, you have different sizes of them,
Yes.
especially you have a marked difference between two otherwise relatively similar polymers, where the cationic part is the same, and you just change the sort of second hydrophilic part, and you can clearly see that makes a big difference.
Yeah, as we saw, these three, I mean, the bundles in 3-block polymer bisalt mixtures, they have different size, and we have in these 3-block polymer, we have the same PAMTMA block, right? They are roughly in the same length. As I mentioned before, the bundle structure, this hexagonal package structure, the PAMTMA only penetrate in the outer layer of the bundle. Then the toroid we found in this 3-block polymer system, they are different, which means this non-charged block play some role in the formation of this toroid structure. Now, if we consider compared to polynipam block and MPEG block, polynipam is more hydrophobic, relative hydrophobic, and MPEG is more hydrophilic, right? This is also seen if you look at figure 2B and C. B and C is polynipam, two shorter block. We have quite a smaller toroid than MPEG. This could be because polynipam is more hydrophobic. Then they are, I mean, compared to MPEG, they are not so flexible in the solution. Then for MPEG figure 2A, the toroid is quite big. MPEG is very hydrophilic, then it can free in the solution and form this big toroid. Another thing is that this big toroid, you can see the internal structure, because large size, you can really see the internal structure. But the small toroid is too small, you can't really see the internal helices. And we were thinking this big toroid from criteria measurement, sometimes I see this big toroid like they closed. I mean, we can't see the end and starting point sometimes, like they closed toroid. And sometimes I see this toroid rolled up by this little bundle, like you rolled up by the bundles. So which means this large toroid can form other close by the one big bundle close, or rolled up by this small bundle. But for the small toroid in the polynipam case, since it's too small, we don't really know. They can form like from this single helices, like a spool up several times or 2 times. Then they form this small toroid, or they can form like directly from amount of material in the local position. Then they form directly this small toroid. So which means we don't really know how the bundle, large bundle or small bundle they form in these mixtures.
Yeah, but you also have always these mixtures. I mean, brings us maybe almost to the beginning back. Is there a way that one can say, well, I push it completely to the toroids, or push it away from the toroids by either preparation, composition.
Yeah, you mean separate this two.
Either separate, or I mean, again, bringing a little bit to the mechanism, because I mean, you see never really pure toroids.
Yeah,
you see sometimes very rich in it, but it's sort of
never pure toroid. We see a pure bundle and coexist of bundle and toroid, but never toroid, which means they have to equilibrium with each other in a friendly way in the mixture.
Apparently, and nonetheless, it would certainly be interesting to tune.
Yeah,
if one can tune it, or maybe even then push it by tuning completely to one side.
Yes, in this MPEG polymer, we actually also did another charge ratio in supporting information. Let's see, supporting information. As I mentioned before, at low charge ratio, we have single helices, right? Then in supporting information, figure page 158, supporting information, figure S15. Figure S15, you see this is the PEG case. PEG case, this criterion is from charge ratio 0.5. And in this low charge ratio, we also see this toroid. You see this toroid that looks like rolled up by a small bundle. And also we see many single helices in this case, which means in PEG case, at low charge ratio, we have coexistence of single helices, bundles, and toroids.
Yep.
So maybe in PEG case, if we go to high charge ratio, in PEG case, we only did charge ratio 0.5 and charge ratio 1. We didn't go to charge ratio 2 or 4. Maybe we go to high charge ratio, we could see some differences. But we didn't do this. This polymer is quite a pressure, little amount, so we can't do so much experiments for this.
Yep, sometimes limitations.
Yes.
Maybe now a bit for other direction. When you were looking now, you basically were sticking in the publication here mostly to one type of polycation. But one could imagine that of course, we're showing polycations, you would also have a lot of variety. Any idea, or did you ever try what happens maybe with different polycations? Of course, double hydrophilic comparable, as you point out, it requires when definitely dedicated synthesis. But in general, if you would stay to the homopolymer and want to compare, that would be easier, because when you could go for vinylpyridinium, ionines, and so on, there are plenty available. The question would be, is that really interesting, or is it more generic that you say, well, it doesn't really matter so much in the structure? Sometimes you have, sometimes you don't.
You mean the charged part, charge block?
The charged part, is that for the dye block, it's maybe a bit more challenging, because you must then have a proper synthesis to do it. For the homo one, it's usually easy, because you just have to polymerize, and they are easily available in different ones.
First, in this, we did one, in order to see this PAMTMA effect, right? We did this PAMTMA 130 homopolymer, then we only see this single helices. And that is at charge ratio 0.5, which means we have excess positive charge. Then that is quite stable, like a gel solution. Then when we go to charge ratio 1, then we have phase separated, we have precipitate. So which means this you have to have some non-charged part to stabilize the structure. Then in paper, in my whole thesis, we have two kinds of block polymerite. One is this polynipan PAMTMA, one is MPEG PAMTMA. We have the same PAMTMA block, and we have this bundle structure formed. Then, as I mentioned, that I didn't include in my thesis is this PEO PDMI block copolymer. So which means this polymer charged part is different from PAMTMA. And the non-charged part is also different. But in this block polymer, we also have a bundle structure.
Okay.
So which means it seems doesn't matter the PAMTMA block and also the non-charged block to form this bundle structure. That's why I demonstrate it's a quite a common phenomenon. Once you have a block copolymer with a charge and with a non-charge, you could form the bundle structure. But one point is the relative length between these two blocks could affect the structure formation. Since in our case, all the MPEG and the polynipan block copolymer, the relative length is like PAMTMA is shorter, polynipan is longer. And in another PU PDMI, it's also PAMTMA shorter, polynipan and PPU non-charged longer. We also did some even shorter PAMTMA, the same like a polynipan 48, PAMTMA 14 and 6.
Okay,
So
that means almost
PAMTMA
nothing.
very, very short.
Yeah.
But unfortunately, we didn't do criterion because we are not focusing the whole polymer, right? We did the ITC measurement for these two. The ITC result, I mean, at least the peak in the region, they are similar, but the amplitude, the height decreased. Which means the enthalpy decreased. If the enthalpy decreased, we can foresee maybe the structure formation can change, because the structure formation release water contrails. If you don't release the same amount, then the structure maybe can change. But if we do criterion, we could see if they also form in the very low, very short PAMTMA block. But I think it's difficult, since we said PAMTMA only penetrates in the outermost layer of the bundle. If the PAMTMA is too short, then in principle, the bundle structure can be very unstable. You can't really stable that, since the inner part you have to stabilize by the oppositely charged block. So probably if we increase the PAMTMA block to more than 30, maybe we can have a growth of the bundle or growth of the hexagonal of this bundle. As you said, maybe they can grow in this, instead of flat, they can grow maybe in the perfect hexagonal phase. But this has to be tested.
When you were comparing also to the SDS, which is of course a very simpler or much simpler surfactant. What I was not catching really when I looked at this work in figure 4.3 on page 83, you have this temperature response used, and you mostly show, well, you have first you have a much more organized compacted micelles, as you might expect for such a system. But does that system, when at high temperature, phase separate, or is that still colloidally stable?
Yeah, this block polymer SDS mixture, as you see from figure 4.2, in charge ratio 0.5, above 30 degrees, we have phase separation. But for the rest charge ratio, they are very, very stable. And why charge ratio 0.5 have phase separation? If you go to the, okay, I didn't. So at this charge ratio, we see a 0 electrophoretic mobility at charge ratio 0.5 instead of charge ratio 1. So again, this polymer, they present in like as unimers and clusters. So at charge ratio 0.5, we have a 0 mobility, which means we have some free polymer chain % in this mixture. And if its mobility is 0, of course, I mean, it's charge neutral. Then increased temperature, they have a high tendency to phase separated. And why we have like a very stable mixture at charge ratio 1 instead? In principle, charge ratio 1, you expect a charge neutral mixture, right? It is because, as indicated by ITC measurement, at charge ratio 1, we already see the interaction between polynipan block and SDS, which means when SDS bind to polynipan block, polynipan become negatively charged, then we have this repulsive force to stabilize the structure. And charge ratio 0.5, PAMTMA was neutralized by SDS, then the free polymer chain in the solution, they don't associate with that.
I was mostly asking when I look at the scattering curve, when very often if you have a skew to the -4, it indicates that it's already big, and often indicates that it, when in the end, will become bigger and bigger, and then finally precipitates. But you have, of course, a good argument that you are already charging, so you just form something big.
Yeah,
and,
from some big
it
structure.
is already colloidally again restabilized.
Yeah, yeah.
Well, then I would probably move to a bit more general questions towards the end.
Okay.
Because you mentioned a couple of times as a motivation, and also today here in your talk, the issue of sequestration of bile salts, which then is of course not a topic covered here because you did a fundamental study, and sequestration of bile salts in my body, for instance, is definitely a medical question, which is a very different one. But nonetheless, just for some ideas from your side, what would you think could be visions of using maybe the knowledge you gained with your systems in terms of maybe at some point also saying, well, this could be relevant for really an application in the medical field?
Yes, since we form this bundle structure at room temperature, right? At different charge ratios like polymer excess, we also can have bundle structure, which means in this bundle structure, a little polymer chain can carry a lot bile salt molecules, which means, and they are water soluble. If you think about, you eat some polymer, then they can, your excess bile salt in your body can bind to a little amount of polymer, and it's water soluble, then it's easier to remove from your body. For sure, this is quite interesting to test this as bile salt sequestration, but this has to do with the collaboration with maybe biochemistry or medicine chemistry to test the binding affinity and also the binding efficacy, something others. And one good thing is that this polynipam pamtma block polymer is biocompatible, as Professor Bu Nistam already tested the catotoxicity. It's relative low, depends on the variation on the block length, and because he did some gene delivery applications, which means it's very, promising to do this kind of application. Then another interesting point is, as you see in paper 3, we did the thermoresponsive study, right? And we get the conclusion that at very high bile salt concentration, and the phase transition decreased to close to body temperature. And for in some mixtures, we have phase separation, right? Which means you have this mixture at room temperature, right? You form this structure. When you eat, the temperature will change to body temperature. Then you have a lot of phase separation, or a lot of bile salt bind together, even more bile salt bind together at high temperature. Then it's even better to be used as bile salt sequestrations if we think about this. And we can use like a different modified polymer 2 block lengths to adjust the temperature exactly to the body temperature. We are close to body temperature 36, 34, but you can adjust by this composition to exactly body temperature to do this kind of application.
Okay, no. Well, I think
another kind of application could be, we did a little test in paper 2. We use bilirubin as a modern drug to test the drug loading ability, and by using this chirality beneficiation, then you can maybe load some ARCA molecule inside this bundle to deliver the drug, ARCA drug, or some chiral molecule, hydrophobic molecule, hydrophilic molecule. Then this kind of structure can be useful for the biomedical applications. Yeah,
sounds convincing. Well, then maybe to my really last question, which I might pose or comment. What would be your idea? I mean, when looking at your last paper, we didn't touch much on this chiral systems here so far. One could also probably discuss here at least half an hour or so, but we will skip this. But maybe just one question. I mean, you do their chiral recognition, and you show that, especially in the ITC curves, either 6 or also a bit before, on page 248 that this is selectively differently binding. Which means there is a different affinity. Could you also think about how this could be used for separating, sequestrating molecules by using the different Gemini surfactants?
Yeah, yes, this is actually a kind of application in this Gemini, especially, yeah, as far as I know, Gemini's surfactant, they form conservation by using other additives like surfactant or some other molecules. Then they can do some like treat with water, which means that they can trap some molecule in the conservate phase. Then it's easier to remove. One interesting in our case is our Gemini surfactant is Chiral. It's Chiral Gemini surfactant, which means, and we form conservation, which means we have a conservation with chiral environment. Then it's even better to trap some chiral molecules, small chiral molecule inside the chiral, the conservation droplet, and you can trap different chiral molecules with different chirality, because we have S and R, and we can also adjust the chirality by different composition. So which means it's very versatile. I mean, you can according to your need, you can adjust the composition, then you can trap or encapsulate some different molecules in the conservate droplet.
Yeah, sounds also interesting. I mean, you have a split. I think probably the challenge there is to have a split between the two as large as possible in mixing ratios, but it's already a convincing ones visible.
Yes, our conservation is very large composition. I mean, from charge ratio 0.3 to charge ratio 3, which means you can adjust very narrow interval to get this conservation phase.
Yep.
Yeah.
Well, as I already indicated, one could discuss long further, but I think from my side, I'm more than satisfied and don't want to spend one more hour here, even if it is a lot of entertaining. I must say, this was just watching here, going very quickly
afterwards.
Yeah.
Yeah, thank you.
Thank
so
you very
much
much for this discussion. It was an excellent one, and very happy with it.
Yeah, thank you very much. So now it's the committee. I will stand here, I think. Oh, I will sit here. Maybe stand here.
So then this microphone is working again. Thank you, Mikael, for this
now.
very nice and interesting discussion with the candidate. We will now let sort of this thesis be more open for a discussion from the public. But before we do that, I would like first to ask the grading committee if you have any particular questions that you want to discuss with Guanqun. So, and I think I made the order that we start with Diganit, and then I will turn to Karen, and finally to Per. So Diganit, you start if you have any questions.
Yes, well, before the questions, I want, even though we're still in the test, I want to congratulate you for what you have already accomplished. First of all, I very much enjoyed reading the thesis. It is well written. You used a very impressive approach to address rather complex self-assembly processes, and you applied a nice combination of high-end techniques. And the outcome, this series of papers is really, really also very nice. So congratulations for this point.
Thank you.
I wanted to, I have two questions. Basically, it was already addressed in your interesting discussion with Michael. I want to, one is about the toroids. So if I understand, in your system, you have bile salts. You mix it with different types of polymers.
Yes.
Okay, homopolymer and an amphiphilic polymer. And you have supramolecular assembly. So you have various levels.
Yes.
The helices, which, if I understand correctly, you said are formed only by the bile salts.
Yeah, in a bundle.
Okay, so if you just take in the bundle as well, only by the bile salts.
Yeah, the inner part of the bundle. Yeah.
Okay, so can you really specify what is the contribution of the different building block of the polymers to the supramolecular assembly, either in the form of very long bundles or toroids? The fact that you can introduce like an angular tilt in the structure is very unique. So it has to be very specific interactions that lead to this.
So in the homopolymer pumped homopolymer, we see only this single helices, right? And that is at charge ratio 0.5, we have excess positive charge that can stabilize that single helices. But at charge ratio 1, we have phase precipitate, which means we have to have some non-charged block to stabilize the structure. Then in the block copolymer case, since we in the bundle, let's see the bundle structure. In the bundle, since we see the interhelix distance is always 5.5 nanometer, and this distance is almost the same or exactly the same as the pure NADC liquid crystal phase at 150 millimolar. And in our block polymer case, the bisalt concentration is only 1 millimolar. It's much lower than CMC. But in the liquid crystal phase, hexagonal phase is 150 millimolar, but the interhelix distance is the same. Then we think the inner structure of the bundle is only self-assembled bisalt. And since the PAMTMA block in our block polymer is only, the polymerization degree is only 20, so it's too short to penetrate to inside of the bundle. That's why the PAMTMA block is only penetrate in the outermost layer of the bundle structure. Why by this electrophoretic mobility, electrostatic interaction, then the polynipam block has to be on the surface to stabilize the bundle. Otherwise, I mean, our bundle structure is quite large. Otherwise, we will have phase separation. We don't see the phase separation, which means the polynipam has to be on the surface to stabilize the structure. Then another evidence or another demonstration is we use NMR measurement. We measured the pure bisalt and the pure polymer and the mixture. Then we see from the mix, then we can compare the signal, where is the bisalt, where is disappear, or then in the mixture, we see there's no any signal in the mixture in MR curve. And the characteristic peak of the PAMTMA block and polynipam block can be seen in the mixture, but polynipam is almost the same as pure block copolymer, the height of the diffusion, the peak. But PAMTMA is almost vanished, but there's a little left in the mixture, which also verify our model that polynipam is in the surface, free in the water, free in the bike solution. That's why we can see the signal in NMR, but PAMTMA, maybe there's in the outermost layer. That's why we see a little signal in NMR, but bisalt, they stuck inside the bundle. That's why we don't see the signal from NMR measurement. This is for the bundle. Then for the toroid, let's see the big toroid, since we see the internal structure, right? For the toroid from cryo-TM measurement, sometimes I don't see, I just see the big toroid closed. I don't see any end or starting point, which means, I mean, we don't know the toroid from the bundle they closed. Then sometimes I also see the like a toilet paper structure from side view. You see the toroid, the big toroid rolled up by a small bundle. which means the toroid can be also formed by this rolled up from the little bundle. Then I can see the end point and the starting point. But since from tomography measurement, the cross-section of the bundle, the interhelix distance is also the same as in the flat bundle, which means, I mean, the inner structure of the bundle is the same as in the inner structure of the toroid is the same as in the bundle. So in the toroid structure, polynipalm is also on the surface. The pamtma penetrate in the outermost layer. But for how really exactly the bundle, small toroid and the big toroid, how they really, why they form, why they equilibrate with the bundle structure, we actually don't really know. Since we have to do like synthesize a series of polymer, keep one parameter, change another parameter, maybe we might see the clue for this mechanism. But for now, we don't really know why we have both in some of the mixtures. Yeah.
Okay. Do you know how long it takes your system to reach equilibrium?
Sorry, I will. Then I will close this first. No, what happened? Yeah. Okay, sorry. Yeah. In the mixer, when I prepare, I mix from 2 stock solution, and I add some excess water to reach the charge ratio. We keep the polymer concentration as constant. Then we change the bisalt concentration to reach the charge ratios. Then after I mix them in the room temperature, I move the solution to the cold room to stir like overnight 24 hours. Why in cold room? It's because this polynipalm is a thermoresponsive polymer. Even though at room temperature we don't see the, I mean, phase transition is about 36 or 35 degrees, but I want to let the polymer dissolve very well state to interact with bisalt molecule. That's why we stir in the cold room like 24 hours. So then we didn't do actually this kinetic study, for example, 1 hour by critiam or 10 seconds by critiam. As Micah suggests, we could do stop flow measurement to really know the kinetic formation. But for the this is after 24 hours, we did the criteria for different charge ratios. That's why we can compare that, because we keep the equilibrium time. But we also did some, like repeat some criteria after maybe half year or 3 months, 1 month, we have the same structure. We don't have like apparent changes in the structure or something. So I think it's quite stable and in a good equilibrium time. Maybe after years, I stored actually the solution in room temperature can be for several months. If I stored in the fridge, can be like 2 or 3 years. I mean, I have old solution from the first year of my PhD study. They are still clear and no phase separation.
Okay. Okay. So you convinced me that you do reach some steady state in your system.
Yes.
If I may, I want to ask another question about a different chapter.
Yeah.
That about the Gemini surfactant with the bisalt.
Yes.
Page 238. Where you play around with the chirality and have different enantiomers and racemic mixture. So did you see any significant difference between your enantiomers?
You mean S difference between S and R and the racemic,
Yes.
right?
Yes.
We do see the difference if you look at the page 242, figure 2B, figure 2B, and also the ITC result, also figure 6B, 6A. Let's see figure 2B first. If you look at the figure 2B, you see this red curve and green curve and black curve, right? Red curve is the racemate S with bisalt. Green curve and black curve is Gemini surfactant R. We see a shift, right, in the turbidity measurement. And this shift is quite narrow in turbidity measurement and we didn't see the difference between racemate, this black curve, and the green curve. In principle, theoretically, since racemate is a one-to-one mixture from S and R, so in principle, in the turbidity measurement, we should see the black in the middle, then red first, then black racemate, then green, right? But we didn't see that. It's because turbidity, maybe the sensitivity is not as good as ITC measurement. ITC, since we touch it droplet by droplet. That's why we see this theoretical or expected shift in ITC measurements. If you look at figure 6A, you really see the shift between these three Gemini surfactants. And the S seems like react faster than racemate and R. And why S react fast, as Mike already actually mentioned, they might have some like how to say favorable interaction between S and the bisalt molecule. And for R, since if we look at the molecular structure in page 238, figure 1, it's not so clear in the thesis. This hydroxy group in S is hydroxy group in S and R, they are in the opposite direction. That's why I show opposite chirality, right? Which means bisalt prefer to interact with S. S is left or right-handed. I never remember S is left or right-handed. So S is left-handed Gemini surfactant. Bisalt interact with S with left-handed Gemini surfactant like to interact with left-handed Gemini surfactant. And if you see the molecular structure of bisalt, of course, I didn't draw this bisalt in this flat way. I draw this bisalt in this this shaped way. If you look at, I don't know if my understanding is correct, since we haven't discussed this so much, this difference so much. If you look at, I don't have this bisalt structure in this flat way. If bisalt structure in flat way, the two OH group, this hydroxy group, they will show the same direction as S. This two OH group in S is towards inside, right? This inside. Then in bisalt molecule, if it's in the flat molecular structure, 2H group also in the inside. I don't know if this is the reason they have a same this hydroxy group. They are in the same direction, which means they can match well than the others. If in R, the OH group in towards this direction, but bisalt OH group towards that direction, they are in a different direction. I mean, the hydrogen bonding effect can be difficult or can be different than S. But this is just my understanding. I didn't dive inside to this point very much, but we should, we should do maybe further exploration for this. But thank you for this question.
Okay, all right. Thank you very much for the detailed answer. And just one last comment. It was very clear in your discussion with Michael that you have done much more than you show in the thesis, which already is very impressive. As I said at the beginning, I think it is very important to document all that as well. One way to do that is maybe through appendix that you add to your book. So all this knowledge, even though if it's not published and it's only maybe preliminary or partial, it is preserved, and,
yes,
other can learn from it.
Yes, this is definitely, because the other work, I don't have enough time to write a decent manuscript to put in my thesis. If I can, I will definitely to put my thesis.
Maybe we can have thesis number 1 and thesis number 2. All right, thank you very much. Thank you very much.
Thank you very much.
Thank you, Diganit. Karen?
Yes,
you want to
thank
have
you.
some
I
questions
would
also?
really, I would really like to echo Dagnit in saying that it was a joy to read this thesis. It was really thorough and very interesting. And I've been very impressed in the discussion about, as she said, the amount of extra work that you've also done that isn't in the thesis. So I would also back up her comment. That would be really nice to have a record of that somewhere if it's possible at all. I was really interested, I think, in the heating experiments that you did.
Yes.
And I was looking at, this is page 177, I think, in paper 3.
Yes.
So you talk about the different charge ratios, and obviously when your charge ratio is 0.67, your electrophoretic mobility is almost 0, and so there's no charge, and the complex precipitates. But
Yep.
then at 0.8, you regain a stable solution, and then at 0.89, it's unstable again.
Yes.
So could you just go through a little bit in detail what's going on with 0.8 and why is it so special that once you've reached, I mean, I can understand that maybe you then start to charge up again, but then if you add even more charge, it precipitates again. So it seems like 0.8 is somehow special.
Yeah, this has to do with the concentration of bisalt. Let's see the bisalt concentration in different mixtures. So in this mixture, charge fraction 0.67 is charge ratio 2, right? It's because we have zero electrophoretic mobility. Of course, we have high tendency to have phase separation at high temperature. This is reasonable. Then for charge fraction 0.8, which is charge ratio 4, then the corresponding bisalt concentration in this mixture is, let me see, is 7.85 millimolar. And this concentration is just about the CMC of bisalt. And we have negative electrophoretic mobility at room temperature. And if you look at the figure 4, when we increase temperature, the electrophoretic mobility decrease to very negative value, which means we have quite a good repulsive force to stabilize the structure. And why it's stable, it could be, I mean, at charge ratio 4, even though it's over charge ratio 1 and the bisalt concentration is just above the CMC, which means we could adopt some extra bisalt molecule can attach on the surface of the structure. That's why they have a negative mobility at low temperature. Then when you increase temperature, then you have a dehydration of polynipam, that rearrangement in mixed complexes. Then you have more release of more bisalt come from inner to outside, then stabilize the structure. Then for this two highest charge ratio, charge fraction 0.89 and 0.89 and 0.94, right? Which corresponds to the charge ratio 8 and charge ratio 16. In these two mixture, the concentration of bisalt is above, they are above CMC. They are like, let's see, they are 16 millimolar in 0.89 and 31 millimolar in 0.94, which means we have much excess bisalt molecule in these two mixtures. Then we can have a higher ionic strength, or we can have some like because these two mixture at room temperature, we already see from static light scattering, we have quite a big aggregate form at room temperature, right? Then when you increase temperature and we have excess bisalt mass cells, then can due to this ionic strength or the depletion effect from this bisalt small molecule, then push the big aggregate even to aggregate together. Then they phase separated, then they have precipitate. If I believe if we go even higher, very, very high bisalt concentration, we will not have any aggregates, maybe dissolved or something.
Okay, so if you go even higher, you would expect everything to precipitate even at room temperature. or you would expect the bile salt
No,
to then
if I go even
break up
high,
the aggregate?
at room temperature, I think the structure could be dissolved by bisalt micelles. In principle, for example, we have 150 millimolar bisalt in the mixture. In principle, you have pure bisalt solution.
Pretty much, yeah.
Yes, yeah.
Okay, so that makes sense now. So I was curious in figure 3 there on page 176. These are heating experiments done on the same solutions that you had in the previous paper, where you have the mixtures of tapes and globules.
Yeah.
Are these solutions, have these been filtered, and or if not, because normally when you do DLS, you pre-filter a sample to take out dust particles. So I'm curious to know here whether or not maybe these solutions have been biased towards having large numbers of tapes and fewer particles, or whether they are the sort of neat mixtures which have both the globules and the tapes. And do you think that there's sort of some effect here on your DLS just due to your preparation methods for DLS?
Yeah, yes, actually for DLS measurement, we do filter the solution by this 0.45 filter. So which means if according to paper 1, after filtration, we only have this tip-like structure, probably at room temperature that we have this tip structure, we remove or not remove, the globule disappear, then in light scattering, the signal could only from the tip structure.
But you have the two different peaks that you sort of link to two different structures.
Let's see. You mean
the slow mode and the fast mode?
Yes. Yes. This is I think in the supporting information, right? You mean figure 3A, right? Figure 3A, the inset.
Yeah.
The inset, yes, we have, yes, at room temperature, if you look at page, if you look at the supporting information of paper 1. Paper 1, page 130, figure S4B. So we have like a bimodal here. Since after filtration, we didn't see the global structure. So this bimodal point to the tip structure. But since the tip is very large, the light scattering, they can't maybe detected by in the light scattering range, but some of the short tip could be detected and in this slow mode. Then this fast mode, for the first time, we explain as this in page 131, second paragraph, we explained as this internal motion of the tip-like structure. Even though we didn't find the references for this kind of explanation, but we believe it is because of this bending or thermal bending fluctuation from this tip-like structure, the internal motion. And the slow mode is from this from some shorter tip structure.
So did you ever try DLS on something which either wasn't filtered or had a much larger filter, just to see whether you could see contributions from spheres versus or globs versus tapes, because it might be an easier way to a quick and easy experiment to do to track how much of each of those structures you have present.
And yes, this we could do. And another thing is that in this paper 3, we did scattering by this Malvern measurement, so which is scattering angle is 173. So at high angle, which means the form factor, our structure is quite large. So in principle, you are measuring some shorter tip at this angle. We could do by this LV measurement in different angles to really see. And also this this figure S4, I think we did by this ALV measurement, but that is at room temperature. So at high temperature, it's difficult. It's quite difficult to do by ALV since we have some phase separation and phase transition, evaporation from the stacking. So we prefer to not so complicate the system. And also since in a mixture, some of the mixture we have also pure polymer chain coexist, and the unimer, the clusters also coexist, as you can see in the Sachs result. So if we do high temperature by the light scattering ALV, we could like everything come together, then we can't explain the curve, the peak from which is which contribute to the which mode.
Yeah, I was thinking more for the DLS, but for following up some of Michael's suggestions about following where you see the presence of globules and the presence of tapes, rather than at the high temperature where everything gets much more complicated. I would agree.
And another, yeah, I can complement in another system. As I mentioned, this PU PDMI block polymer. We have also big global and the bundle structure in that polymer, and we are able to separate this structure by centrifugation. In the top phase, we only have this global structure. In bottom phase, we only have tip structure. This one we did light scattering by measuring the top phase. We really see only this global, the size exactly match the criteria measurements. And the bottom, I don't remember if we also did the light scattering for the bottom phase. Since the bottom phase, we have to add the water to redisperse the bottom phase to measure. I don't remember exactly if we did that.
Yeah. So the other thing I was wondering about in the effects of heating here were whether or not if you heat up a sample which is largely tapes and then you cool it down again, do you reform tapes? Do you reform a mixture? What happens? Are these heating experiments reversible? And I guess that probably depends on the charge ratio as well.
Yes. If you see the DRC measurement, in the DRC measurement, we did the scan at least 2 times, up scan, down scan, up scan, and down scan. During each round, up scan, down scan, then we wait for 5 hours. No, let me think. Anyway, we did up scan, down scan, up scan, down scan. So all the 2 up scan, they are the same. The curve shows the same, which means after cooling, the solution come back to the previous state. But we didn't do a criterion for after heating for the measurement. And some of the sample, if I remember, some of the precipitate sample, they can't, I think they can't reverse, as we did NMR at high temperature, then they precipitate at high temperature, then they don't come back. I saw the precipitate in the tube. But in this longer block polymer case, for example, the high charge frequency 0.8, they don't precipitate. Then we increase, decrease, the solution become clear. So we don't have, it's reversible. Yeah, but we didn't do criterion again after heating. But we should actually to test if the structure reform come back from the big aggregate at high temperature to change to the tip structure after cooling. Then it means we can control the structure formation in different temperature. This sounds very, yes.
I was also curious as to whether or not it would mean that you had more of the toroidal structures, because if it starts from being a glob and then phase separates back out, it might be different, a different set of structures that you get compared, like they might, they're all tape structures, but whether they're toroids or flat tapes, the ratios there might change as well. But just depending on, because they follow different pathways as they form.
Yes. So yeah, you mean the toroid, the big toroid structure in the. Yeah, this. Yeah, we actually didn't do for example, in order to know how really, if we separate the toroid, only have the toroid structure, we don't really do that since we need a series polymer, or we keep the, I mean, have to keep some parameter, then you change another parameter to see the effect. In this 3 block polymer case, they happen at different block polymer and different charge ratios and coexist with the bundle. So it's better we synthesize a block polymer, like control another block in a different length, then we do different charge ratios. We could see some effect.
I was just thinking whether or not the toroid formation is temperature sensitive.
Yeah, you mean that? Yeah, yes. Yeah. Okay. So in this toroid system, this shorter block polymer bisalt mixture, I also did a thermoresponsive study, a huge data. Wait for me to write a manuscript. And for sure, in this shorter block polymer bisalt mixture, the thermoresponsive behavior is different from this longer block polymer bisalt mixture in paper 3. I mean, they show, at least from DSC curve, they show very different behavior. So which also means the block polymer length can have some effect, since we don't have the toroid in this longer block polymer bisalt case. They have this small glober instead of toroid. So yeah, this could be very interesting to maybe from my thermoresponsive behavior in this 2 shorter block polymer, I can find some clue for the toroid structure formation. I don't know.
There's always more things that can be done. That's the problem with science. I guess just one final question, which is sort of I guess, a bit outside the scope of your project, but thinking again about the medical applications. Typically, in medical applications, they're quite worried about fiber formation because they're worried about things like amyloids. And I mean, these are natural bile salts forming the fibers, but do you think that this would be a concern if you're thinking about drug delivery type applications, that these bile salts could go into sort of fiber formation modes and, therefore potentially template other less desirable fiber formations?
Since this fiber formation has to do with the polymer, I mean, bisalt itself at this low concentration, it's difficult. I mean, they have this small mast cell.
But if you're going to use the polymer in
induce this formation at low
it would induce the formation of these fibers. So would that be something that you think in a real system you'd have to worry about, or there's so much other stuff going on that you'll probably only form globules in real systems anyway? Yeah,
I mean, this has to test the bisalt binding affinity and this association and the association, this kind of experiments has to do to see the fiber formation, deformation, and the problem, as you mentioned, if they cause some problem as the lipid fiber or some others.
Okay. Yeah. Thank you very much.
This is a really good point to think about. It's to, if you think about medical application, as you mentioned, this is really important to think. Yeah, thank you.
Thank you very much. And yes, I will just reiterate that it was a really lovely thesis and very well written. So thank you very much for a pleasant reading experience.
Thank you, Karen. And then I turn to Per and invite you to discuss a little bit with Guanqun.
Thank you, Guanqun. I really enjoyed reading your thesis and I enjoyed the discussion here. And I must say I end up with the idea that you really like the science you are doing. Is that correct? Yeah.
Even though sometimes I was suffering, but once I get good result and understanding, super happy.
Yeah. So I just will ask you a few questions. So if you go to paper 1, figure 3.
Yes.
There you show electrophoretic mobility. And you have these structures, you have the globules and you have the tape-like structures, right? So which of the structures do you think contribute to electrophoretic mobility here?
Yes, let me think. Yeah, the as I remember, yeah, I think I mentioned to Maka, he asked why we have this global and the tape. I mentioned from criteria measurement, it looks like the global most likely to be close to the frame. If we think the frame is negatively charged, then the global could be positively charged. Then the global can contribute to the electrostatic mobility because that is slightly positive. And for the tip structure, if we think about in paper 2, our new understanding of this bundle formation, we think about the PAMTMA block penetrate on the outermost of surface of this bundle structure. Then maybe we have some PAMTMA left on the surface that could also contribute to this positive electrophoretic mobility.
So in my view, these tape-like structures, they are so huge, so they would give very, very small electrophoretic mobility. So I would imagine that it's mostly the globular structure which contributes here.
Yes, yeah.
But then I find something very interesting here. Yeah. If you go from x 0.2 to x 0.4, your mobility actually increases. What do you think that is due to?
X 0.2 to 0.5, right? You mean?
Yes, it actually increases.
Yeah, it increased, but if you look at the scale, it's very, very small. I mean, it's within 0 to 1. I mean, if you think about the scale, the increasement is very, very small. And why it's increased? Let me think. Yeah. Why it's increased at charge fraction 0.2 from Sachs measurement? We know we have the coexist also the polymer free chain and polymer clusters. And if you think about those, can't contribute too much to the light scattering because it's too small to detect. But at charge ratio 0.5, we have more aggregate formed, and charge fraction 0.5, we have more aggregate, and the free polymer chain and the cluster, they decreases. They still coexist, but compared to charge fraction 0.2 amount, they decreases.
Yeah, so I can see two reasons for this. Either that actually your globals shrinks a little bit when you add more bile salt, or the other thing which could be more interesting is that the bile salts actually prefers to go into the tape-like structure, so you get higher positive charge on the globals. I don't know which one is correct, but it's related to what you discussed with Michael here, that
yes.
Do you have the same composition or not?
Yes, yeah, yeah, the composition question is always interesting to explore, but for now, in my thesis, it's difficult. Yes. Unless we really separate them, maybe we could see the composition, but now they coexist. Yes. So it's difficult.
Okay, so then if you go to paper 2, there you conclude that if you add salt, you weaken the interactions between the copolymer and the bile salt.
Yes.
And that's, I think, is natural. But if you would like to use this to capture bile salt in the intestine, do you know what pH and what ionic strength you typically have in the intestine?
The pH, yes, this is a good question. I guess in the stomach, we have quite low pH.
In stomach, it's quite low, but in intestine, it's actually quite high. It's typically what I have seen is they report somewhere between 5 and 7 in the intestine. So then you are basically right. But the ionic strength is typically quite high. I have seen values from 70 millimolar to 170 millimolar. Probably depends on what you eat and all these things also, but it's quite high.
So which means since we test this 50 millimolar sodium chloride, we still have bundle, but the bundle become narrow, which means if think about the ionic strength in the intestine at high level, then probably the bundle will dissociate to the single nanowires or just narrow bundle, become narrow bundle.
It could
but
be
if you also think about in the body, the temperature is high. I mean, the
Exactly.
temperature is high temperature and the bundle structure could change
Yes.
to big aggregate. If it's a big aggregate, they can also adopt more bisalt molecules.
Yeah.
Maybe we don't, in the bisalt questions, in the body doesn't matter so much how the co-assembled structure. The importance is that you can adopt more bisalt to remove excess bisalt molecules.
Yeah.
But this is the interesting point if we do the thermal responsive behavior in different salt concentration, we could see the effect.
Right. So that will be interesting following up to an already very interesting study you have now.
Yes.
Okay, so my last question then, when I read paper 1 and paper 2, I think I understand really the details of the structures you form, and it's a really beautiful work.
Yeah, thank you.
Paper 3 is also a good work, but here I do not really get the same complete understanding of what structures you form at high temperature. And I do not understand how this tape-like structures is converted to these large aggregates you see at higher temperatures and so on. So can you tell me more about that or speculate about that?
Yes. This is a very good point. In paper 3, actually, at the very beginning, since we see the tape-like structure at room temperature, right? This structure, we actually tried cryo-TM at 50 degrees. But it doesn't work. I mean, when you increase temperature in the chamber of this blotting in the preparation procedure, the humidity and everything changed. The blotting become very, very tough. So we didn't. It doesn't work. So we give up for the cryo-TM measurement. Then from the SACs and from other measurements, DLS and light scattering, we think at high temperature, at least above the phase transition, due to the dehydration of polynipam block, then it has to do rearrangement or structure inverse change. Like for example, polynipam in room temperature is on the surface to stabilize the structure, but at high temperature, due to the dehydration of polynipam, then polynipam has go inside of the aggregate. Then PAMTMA has to go from inside to outside, then bisalt, since there's no obvious interaction between bisalt and polynipam, then bisalt molecule has to also go from inside to outside to interact with the PAMTMA block outside, which means if we think about it's a core shell structure at a high temperature, then the core has to be the dehydrated polynipam block, then the shell has to be the PAMTMA block with binded bisalt molecule. If we change different charge ratios, then the charge on the surface can be different to stabilize the aggregate.
Yeah, so it must be very dramatic structural changes going on here.
Yes.
Temperature. So are you sure that bisalt doesn't interact with the NIPAM at high temperature?
Yeah, this actually also discussed with Maka. So at least at the beginning from ITC measurement, we doubt because we see this high amplitude or we see something. Then when you compare with the SDS case, since as far as I know from the literature, if there is strong interaction, then if there's strong interaction or binding, then the CMC in the polymer should decrease to or should shift you should have a CAC value or CAC number in the percent of polymer or block polymer or homopolymer, which happens in the SDS case. In the homopolymer, we see a small CAC value, which is around 1.5 millimolar. Then the CMC of SDS is 8.6, which is clear SDS bind to bind to polynipalm homopolymer, right? Then in the bisalt, in the block polymer bisalt case, we didn't see a CAC number. Instead, we see this this peak value, or the peak value is even shifted to a little bit more bigger than the CMC of bisalt in water. The CMC of bisalt in water, let's see, the stable CMC is 8.4 millimolar. Then the peak value in the percent of homopolymer is 8.6 millimolar. So if the CMC in the percent of water and in the percent of homopolymer doesn't change, I can see there is no obvious interaction, or at least no obvious binding between polynipalm and the bisalt.
But this is at the room temperature, isn't it?
Yeah, this is at 25 degrees.
Yeah, so if you go to higher temperature and the napalm becomes more hydrophobic, then
yeah,
you could think
probably,
that you could have some interactions at higher temperatures.
Yes, yeah, probably we should have. But I also doubt a little bit, because if we think about the DSC result from paper 3, the DSC, this also has to do to compare with SDS case. In DSC result, the DSC result in paper 3, if you go to the page 179, when we add the bisalt, right? When we add bisalt, the transition temperature of block polymer decreases to close to 33 degrees, which means the polymer become more and more hydrophobic. If bisalt interact with polynipalm block, we will have a more excess negative charge, which means polynipalm will become not so hydrophobic. Then the transition temperature will increase. This is the case in SDS system. If you look at the figure in paper 4, the DSC measurement figure 220 page, figure 7, it's clear in DSC measurement the transition temperature increases at charge ratio 1 and disappear completely, which means SDS, due to the interaction between polynipalm block and the SDS, the polynipalm become hydrophilic completely with this negative charge, and your transition temperature increase to very, very high the temperature. In principle, SDS changed the polymer to completely hydrophilic polymer. Yeah, this difference make me believe the interaction between bisalt and polynipalm is very poor, or almost no interaction.
I agree. You have good experimental evidence for that. So thank you very much. That finished my questions.
Thank you very much.
Thank you, Pam. And then I will ask if there's anyone in the audience here that would like to ask questions. I'm turning first into lecture hall A. I see not many hands waving. On Zoom, is there anyone? There was one way. Okay, so wave. So Björn, you have a question.
Yeah, you can.
Okay. No, I'm very deeply impressed by not only the book you are presented, but in particular by the discussion you had with
Thank you so much.
with Michael and the other committee members. It was a very nice and discussion. I have just one comment, and this is that my experience on some students I had working on polyelectrolyte surfactant interaction, and this is that about equilibrium. Sometimes it doesn't help just by waiting. It's and I was relieved by some experiment you do to reverse, but we encountered something. One student I had with Ulf that realized that even waiting for 4 years didn't help to get equilibrium. Okay. So, but then he was Jonas. Then he invented another mixing protocol, and sometimes this can help when if you mix in different ways, and it's not so always so trivial to find out what is equilibrium, if you at all find equilibrium. And our experience with DNA surfactant was that equilibrium was not always easy to reach.
Yes.
So congratulations, was excellent work.
Thank you so much.
Thank you, Björn.
Thank you.
Is there anyone on the Zoom who would like to ask a question? I think you just have to speak up and then.
No questions?
No. What we do then now is that we close this part of the open dissertation, and the committee members will now withdraw and try to discuss and come up with a verdict for Guanqun here.
Okay.
So, and we will then go to another Zoom link, and I hope that all three committee members here have this Zoom link, and we will meet you there in about 5 minutes. So thanks again all for the very nice discussions, Mikael first, and then also with the committee members. And I don't know what we can do some applaud here.
Thank you for all your. So we leave, then we come back.
So now we will do like this. We will mute.
Mute myself. Mute.
Tiganit, are you there? You have to.
Hi, yes, I heard you, but you didn't hear me.
You have to use the other link that I sent to you.
Okay, I will do that. Okay.
Sorry, we have a noise problem here.
Hi, this one. Karen? Hello again.
Hello. We need Guanqun here, at least. There she is.
Microphone?
And the microphone.
It's on. Mine is on. Yeah, your microphone?
No, it's
Yeah, you can use that. Yeah, maybe, I don't know.
We could hear you better before.
Can you hear me?
I can
Can you
hear
hear
you,
me?
yes.
Do you hear me now?
It's
Better, yes.
yeah, it's on. No, it's maybe
Yeah, it's okay now.
it's now it's
Now.
on.
Do you hear me now?
Yes.
Yeah. Okay. So now the chair of the committee will give a little speech. Karen Edler, please.
Thank you, Karen. Yes, so on behalf of the examination committee, I was elected chair. So I'm Karen Edler, and Agnit and Per. We had a really nice discussion with Karen and Vivica, and also with Michael, about Guanqun's performance. And we would again like to reiterate that we thought that the thesis was very well presented, and a really lovely example of a great deal of work and effort by the candidate, and it's been expressed really well. We had a lot of really interesting results shown in that work. And then we'd also like to say a thank you to Michael for his work as an opponent, particularly with Guanqun's very fluid answers, and the fact that she didn't seem at all nervous, at least over Zoom, and was able to explain her thesis really well, and very fluently, and knew exactly where everything was in her thesis. So we would like to congratulate Guanqun and say that we have unanimously decided that she should pass on this, and also congratulate her supervisors for a wonderful job at supervision, but particularly to Guanqun, very well done. And we hope that this really launches a really good scientific career in the future.
Thank you very much. I'm super happy I passed.
So let's see now. Let's see.
Congratulations.
So do you hear me? Yeah. Okay. Thank you very much also to the committee and to Michael, the opponent, for this great effort to read and also have these nice discussions. That we have a lot of things to do.
Yes.
And now, since we are all gathered here, still waiting, people are here, 19 persons. I take the opportunity. We don't have, usually we have snacks and celebrations, but there are some gifts that I would like to present from your colleagues at the division has collected this gift for you.
Thank you.
And it is in a card.
Yeah. Can I open now?
Yes, you can.
I will open now. Oh, the pink color. Don't want to store this.
You can show it.
Oh, lovely. Very beautiful. Please. It's a it's a gift card.
It's a gift card. And I think you are at this sports shop.
Yes.
Where you have some special
Yes, I can buy some exercise stuff.
It's time now for the
It's
after-
time to exercise. After a long preparation of thesis and lack of exercise.
mental exercise, and now you have to start with the
Physical exercise.
And it comes also then to the natural, very classical gift
Yeah.
that you all guests and PhD students that
Yeah.
leave or come and leave and come
Yeah.
back are getting from the division.
Yeah,
And it's some kind of sporty sweater.
I will open.
You can do as you like. Yes,
I will open.
you do for we have a.
Yeah.
This is maybe something you can do then when you do your physical exercise.
Yes, yes, yeah. I actually love this kind of casual clothes. I know it's from the university.
Maybe it's something else.
Oh,
who
maybe
knows?
it's a special one.
We wonder what it is. Everybody's smiling who are from the division, because this is something that we sometimes wonder why we don't have when we enter the division. We should all wear
we should
these,
have a uniform for the
uniform.
division. Design a uniform for the division. Physical chemistry. At least a T-shirt with logo.
logo. Let's see
Yeah.
what you get here.
It's a nice color.
You can hold it up to the.
Yeah, I will put here. It's I think it's the hoodie, right?
Yes, it's a hoodie.
I
Yeah,
will
you don't.
open
You want-
completely.
Yeah.
It's a nice color.
Nice color. Wait. Lund University.
Lund University. No, I'm the
Whoa.
doctor from Lund University.
Soon. It's not registered.
I'm
yet.
not registered.
and
Thank you
now-
very much.
And then I have something a little special also that is from me. Because actually now I start to get a little bit moved because we started our journey together actually 1 year before you came to Lund.
2016 in the
2000
fall.
2016, I was approached by an email. No, sorry, it was first an email from Björn Lindman,
Yes.
who asked if I would like to contact a very good student from China that had written to Björn,
Yeah.
and that was Guanqun.
Yeah.
Because Guanqun met Björn in you met Björn in a conference in China,
Yes. Yes.
and then Björn.
Then I wrote the email to Björn.
And then he wrote to me, "Thank you, Björn."
It is actually you forced to bring me here.
Yeah, and then you wrote to me.
Yes.
And
yeah.
I had to think about it,
Yeah.
and I think I thought about it for 1 month or something.
Yeah, we have some back forth through email. Then we have this telephone.
Then
meeting.
yeah, then I had to. No, I investigated a little bit before I contacted you. So I had a special call with Yilin Wang,
Yes. Yes.
who happened to know your master supervisor.
Yes. Yes.
The professor of the in your master university.
Yes.
And they had a chat.
Yes.
And then I had a chat with Yilin, and then I said this is very good. So we started then to speak by Skype 2016.
Yeah, and roughly November, something like that.
And then it took another year before. So we regularly were Skyping for 1 year, and then you came 2017 in October, very dark night with 2 huge suitcases, and it was the first time you traveled abroad.
Yes, the first time I take flight, actually.
First time you took flight. Then during all these years, we have now and then had to be on Skype. So it is something natural for us. Unfortunately, when the pandemic started, it was somehow, although it was difficult, we managed very well through that we were used to speak by computer. Yes. And this will be something that I hope will continue.
Yeah.
Now when you are flying back to China for a postdoc,
Yeah.
in Yilin's
Group.
lab.
Yeah.
I hope we can continue to speak by Skype,
Yes.
and we have to continue to do our collaborations and
Yes.
finish some things.
Yeah.
And that has been something that I will look forward to, and that can comfort me,
Mm.
because it will be a little difficult.
Yeah, but I mean, we are working in this way by using Skype for a
Yeah.
long time, and it worked very well.
Yeah.
So
This is a present, and I found I wanted to write something, a little card. This is a card, and it happened just to be in my drawer, and I have never used it. And I said, but it's some Chinese things here.
yes.
And it's a card painted by an artist that either use his foot or her foot or mouth. It's no hands. And it's called the Pearl of the East, the Eastern Pearl. This.
Yeah.
And I thought you were the Eastern Pearl. So, and then to remember me, I hope you will use this every day when you are eating some soup.
So I will.
You can open.
I can guess.
Yes.
What's that? So then I
It's a
will
little
open.
tradition I have for that maybe other PhD students of mine now
Yeah.
will smile a little bit.
Aha, so
Like,
everyone get.
But it's always a special spoon.
Yes. Yeah.
And in your case, very special. It's not the same spoon.
Ah, I'm curious very much. What's that? Let's see.
This has a little story also.
Sorry.
It has a story.
So, 1 year.
This is, I hope you really will use it every day.
Ah, a really, really special and nice spoon.
And it is from the north of Sweden, from Sundsvall, actually.
Okay.
And it's from 1798.
Mhm.
98. It's an old spoon.
Mm.
So many before you have used it. And you see,
Actually,
silver is good.
I developed a habit here, which I don't have in China. Here, every time when I eat food, noodles or other things, I always take one spoon and a chopstick, then put noodle here, then eat like
Yeah.
this. My mother said, you always have a spoon, but in China, you just use chopstick.
Yeah.
You never use the spoon.
But now you can use my
No,
spoon.
This is the perfect size because the normal spoon is too small, you know, sometimes the noodle soup.
Yeah, this is good.
This
Yeah.
is perfect.
Yeah, it's a little bit bigger. Yeah.
Very nice.
I think we
Thank
came
you so
hugging.
much.
Thank you
I
very
like
much.
it very, very much. Thank you.
Thank you very much. So I also would like to thank you for all these years and all the fantastic work. You have done very good work today, and the work that you have accomplished. And I'm very proud of you, and you should be very proud of yourself.
I'm actually very happy and lucky. I have the best supervisor during my PhD study.
Tell me more later.
The best.
Thank you very much. So I don't know if somebody else would like to say some words to Guanqun. This is the party we are having. This is we will have some smorgasbord cake here. Okay, yes, we have some nice collaborators from far away, from Rome. Luciano is there, and we see some other of the group in Rome. I saw also from China connected one.
And now I know all the committees. So if there's chance to collaborate, yeah.
We will speak about this. We have more to say.
Yes.
Okay. So by that, I think maybe our little ceremony is over.
Yeah. Thank you for everyone.
Thank you.
Thank you.
Bye.
Thank you.
Thank you, everyone.
Thank you. Congratulations, Guanqun.
Thank you, Luciano. Thank you,
Bye bye, everybody.
Thank you. Thank you.
I hope to see you soon.
See you soon.
Bye.
Yeah, we end.
Hi to all the
Bye.
committee. Yeah.
Bye,
Ciao, ciao,
Gani.
ciao. Ganit,
Bye.
Nickel, Karen.
Bye. Bye.
Bye.
Bye.
Ciao.
Boo.
Yeah, congratulations.
Bye, Boo.
I will leave.
Yeah. Okay.
Leave the meeting.